So what is augmented data cleaning?
Say it again.
Yeah, I'm just reading your biography, and it says that you hold a PhD in the field of augmented data cleaning, and I was wondering what augmented data cleaning is.
Okay, this is like a fancy name for, okay, we use machine learning to to develop some data cleaning methods. So practically that's it. And I discovered this term probably 1 year ago, so it's quite new. And I think it was you can find this on Gartner. So it sounds fancy, so I decided to stick to it.
So usual data cleaning is when a person cleans the data, but augmented data cleaning is when there are tools that help to automate this process, right?
Especially if these tools using machine learning.
Okay. So basically detecting some quality issues, right?
Exactly, with machine learning. Okay. In order to prepare data for machine learning.
Okay, yes. So it's like we have machine learning algorithm to train a machine learning algorithm.
Exactly.
Nice. Is it like binary classification? Like for each column you check, has this column some problems or?
So actually this is more complicated. So like in my case, we had many data cleaning tools, and the state of the art of data cleaning tools, like they focus on just one error or just one particular type of error, like missing data or whatever misspellings or outliers, and you have mostly like several kinds of errors, and no one tool is just you can fit it all, right? So and so we applied many tools on one data set and tried to learn from the outputs from these tools, all the whole spectrum of the errors in the data set. So and this, we defined the data cleaning as a learning problem, and it worked quite well.
Yeah, I think you shared a link to your dissertation in some of the threads in our Slack, right? So I think it was asking something about data cleaning, right? And then you shared your dissertation, I think.
Exactly. So I wrote a blockbuster.
Okay, I think we can start now with a short introduction. So I'll just shortly introduce the conference, then I'll introduce you, and then we can start. So thanks everyone for coming today, for joining today. For joining our conference. Today is the last day of our conference, and we will talk about machine learning in production. So we have 4 talks today. So now Larysa will talk about 10 foundational practices of machine learning engineering. Then Mikio will talk about putting data science in production. And then Sara will talk about machine learning design patterns. And then finally, at 5 o'clock Central European time, we will have a last talk about continuous integration for machine learning by Elle. So yes, I think you can start. So maybe let me briefly introduce you. Larysa works at InnoQ, and her current interests are on the intersection between software engineering and machine learning, MLOps. And Larysa holds a PhD in the field of augmented data cleaning. And if you are wondering what augmented data cleaning is, you can check our discussion 10 minutes ago, maybe after the conference, where we talked what this is. And yes, so the floor is yours, please.
Okay, thank you very much. So I'm really glad to kickstart this last day of the conference, and let me share my screen. Where it is? Desktop.
And I forgot to mention that something that is not in your biography, but Larysa started this awesome MLOps repository. So you should, if you haven't seen it, you should definitely go and check. And like you can find here on Twitter, and the link is there. So just check. This is a very like it's a great resource if you are starting with MLOps. There are many articles, many links. So yeah, definitely go and check.
Thank you very much. So you can see my screen, right?
Yes.
Great. Good. Okay, so thank you very much for the introduction and for the introduction of awesome MLOps. All right. I work as a software consultant at InnoQ, and like a software consultancy, my colleagues are often asking me what is the actual difference between developing software, traditional software, and software which contains machine learning. And this is in this talk I gave to my colleagues to explain actually all that stuff. And I see machine learning engineering as a set of principle techniques from machine learning and software engineering in order to design, build, and deliver machine learning based software. And usually I start my presentation with this slide where I explain the difference between programming and machine learning in order to get this distinction clear. So in programming, we have data, we have our program, we put it in the machine, and we get the output. In machine learning, we will need to take an additional first step, which we call training, in order to actually produce this program. And this program is called machine learning model, where we get our data, get the labels or outputs, put it in the machine, and from these data and outputs, we will train the model, which then is used on the new data to produce the output. And there are actually three fundamental components of machine learning engineering, which are data, model, and code. And whenever we have a changes in our data, we will have a change in our code, which probably will, the changes will propagate to the code. And and all these three components need to be so we need to make clear that the machine learning systems will be more complex just because of changes on these three levels. Well, let's go to the 10 machine learning engineering principles, and I organize them as a hierarchy of needs. I think this metaphor is very useful for us. I don't have answer for anything, but I have some experience which I will share with you, and probably this experience will be useful to you too. Let's start with the first and most important question, which we have to ask not only before not only before machine learning project, but also before any software project. Like, what is the business problem what we are trying to solve here? Usually I have the following pattern where people come to me and say, we have so many data, we collected so many data, historical data, we definitely need to apply machine learning on these data. And I try to calm down a little bit this discussion, and first question I say, okay, what is the problem what we are trying to solve? What are the pain points do your users have a pain points with your software? So, and if and then we will go and ask ourselves, is machine learning then the right problem, right technology to solve your problem, to solve your pain points? And usually the rule of thumb is if you have an algorithmic solution for your problem, don't go out for machine learning. Machine learning problems usually we distinguish four kind of machine learning problems or problems where machine learning is a suitable solution. Such problems usually are big, right? So we have more movies outside there than we can watch in our entire life. Machine learning problems are open-ended problems, so we have Twitter streams, video streams, and so on. So machine learning problems are usually time-changing, so we need the systems which can learn with the changes. And usually machine learning problems are intrinsically hard problems. The examples are natural language processing, image recognition, video processing, audio understanding, and so on and so on. So these kind of problems are suitable for machine learning. And you know, the first stage of any machine learning project, business and data understanding, is really crucial. And when I started first in this area, I was looking for practical methods how to actually identify use cases for machine learning, and I found nearly nothing. This was the reason why I and my colleagues developed a method to identify business use cases for machine learning. So what we did, we combined two parts. Our first part is we took domain-driven design knowledge crunching methods. We took event storming method and combined it with machine learning design canvas, which is developed by Louise Torard, and used event storming as I said, knowledge crunching to understand the system, to dissect the system on an atomic level, to understand all processes and workflows in the system, and identify the pain points in our system or problems in our system. And then we will ask or we decide and prioritize these problems, whether they suitable for machine learning. So, and after that, we go and try to prototype the system, the machine learning solution or structure or project with machine learning design canvas. And I really recommend to go for and have a look at the design canvas to structure your machine learning project on a high level. Right, so the machine learning design, this canvas consists of 10 elements, and the central the tower is about value proposition and life monitoring. So we identify or we state what is the use case, what is the problem, how can user benefit from the machine learning solution. And the life monitoring is actually, how do we know that we are doing well? So we try to identify all the business metrics and put it here. So, and then we have left and right part of this canvas. And the left part is about prediction. Is all the aspects of the prediction, what is the prediction task or machine learning task? What decisions are made? And especially interesting is the offline evaluation or impact simulation. How do we know? How can we simulate that our machine learning is getting the value to our customers? And the right part is about data. Is about data or training step of machine learning. So we will come back to this kind of several times in my presentation. So let's move to the next point, and the next point is about staffing. So if you have machine learning project, you will have you will need skilled people, and usually we have the data engineer who work with data sources, curates the data sets, and prepares data for data scientists who looked at the data, trains model, and give these models to MLOps engineer who brings this model into production. And if you look at this, this picture is quite idealistic. So you won't find a lot of MLOps engineers right now. And what we did the following. In my project, we found a DevOps engineer who was curious enough to learn about machine learning. And we found a machine learning engineer who was curious enough to learn about the DevOps and all the procedures, how to bring machine learning into production, how to deploy machine learning. So, and we paired in GIST, and the whole MLOps engineering was done by two people. And they learned from each other, and and they were ready to do this as a pair programming. So this works very well. And this is actually my recommendation how to solve this shortage of skills for machine learning operations. Right, the next point, machine learning project management. The most common or most popular complaint about machine learning projects is because of their ad hocness, right? So because we cannot really avoid it, because machine learning is, because of its nature, experimental. So we have to try out many things also because the data may not give you an answer, and more data may also not give you an answer, and so on. At the same time, machine learning projects are not really well organized. They are not documented. People are working with Jupyter notebooks, so the execution routine or execution cells are messed up, so they are not repeatable, all the experiments. These are most complaints which I get about machine learning projects, but there are already initiatives about how to tackle this problem, and two of them I really recommend to look at. The first one is a cross-industry standard process for machine learning applications, with the emphasis on testing. And they define the 6 project phases and describe the details of what's going on from business and data understanding and through the deployment and monitoring. So I really recommend to get the paper, and it's nice read, and you will get the idea about the project machine learning lifecycle. Another one is a team data science process, which was suggested by Microsoft, and they not only give you the description of a lifecycle, they also give you some templates which you can use, a project template, and this is a structure for your machine learning or data science project, which will give you clear structure to separate your data, your code, and your models and configurations. So have a look at this and try it out. Really nice. I have a good experience with this. Okay, this is a DataTalk.Club conference, so we will talk about data right now. And data is a fundamental part of machine learning because without data, there won't be any machine learning. So in order to get to machine learning, we will need to make sure we have a solid data infrastructure to collect, store, transform, clean or data, to do a feature engineering, and then we will set up our machine learning initiatives exactly on this infrastructure. Back to our machine learning canvas. I told already that the right part is about training, and training is about data. This machine learning canvas will force you to think about what data sources, what raw data we will have or need to have for training. How can we get new data in order to retrain our data? And here, before we start a project, we will have to think about feature engineers. What features do we need? Do we need additional sources for that feature? So this is, so you see that machine learning canvas is a very useful framework which forces us to think about many stuff which are not obvious before we start a project. Well, the next point is about machine learning algorithms, machine learning task, because it's not trivial to translate business problems into machine learning problems, especially if you don't have experience with it. So we have, and this is not trivial because one machine learning algorithm can solve different problems, and one business problem can be solved in different ways in machine learning. And we classify all machine learning according to 3 dimensions, like the kind of problems, the explainability of machine learning algorithm, and the performance. And depending on your experience, on your level, or requirements, you might want to stick with simple models because of their explainability, because they are easy to understand, and especially if you have regulatory requirements where explainability is a must. So you will have to go with the simple algorithm like logistic regression, linear regression, decision trees. But with experience, it's obvious that you will get into the more or higher performance algorithm like deep learning or ensemble methods, but it's not advisable to start with them. Good. The usual way and very pragmatic way to start with no ML solution. And before we start the first translation from business problem into machine learning algorithm, we will need to define the solution, heuristic as a solution, and this will be our baseline. This will be our baseline because this is our first machine learning model deployment criterion. This is important for many reasons. we might need this heuristic in order to persuade or decision makers that yes, machine learning will give you the benefit and will give you value for your software, and like I said, this will be deployment criteria, and there's a nice pattern called heuristic benchmark, which we can apply in our initial as an initial step. For example, if we translated our business problem as a recommendation problem, so we can use a most popular item in our training data as a benchmark, or for example, for anomaly detection, we can use 95th percentile value to identify what are outliers, and so on and so on. And I think you introduced Sara today. So this pattern is from her book, Machine Learning Design Pattern. So I'm looking forward to her talk as well. Well, the next point is about the flywheel of machine learning systems. And when I explain machine learning, when I explain the life cycle of machine learning models, I always tell that a machine learning model is like a Tesla car. With every update, it gets better. Like we have better models, we will deliver better or more value to users. We will get more users, which will get our more data, and more data will update and make our models better. So, and this flywheel, we have to understand this life cycle of machine learning, and this is another aspect to understand here is that the post-deployment of machine learning will be as important as pre-deployment, right? So you will need to set up machine learning monitoring and alerting, and so you will need to monitor not all the usual system metrics, but also the machine learning specific metrics like performance of machine learning model, if you have labels, if you're lucky, and or you can monitor the inference time of machine learning, the input distribution, or what values are produced by machine learning, the distribution of the outputs of machine learning. Because we have this phenomena of machine learning model decay, that means when machine learning is live, the performance usually drops, because machine learning model is trained on historical data and live data, so probably it hasn't seen the data before. So this is why we need to keep the retraining all the time. And if we are pragmatic, we built already our CI/CD pipeline for continuous integration, continuous delivery, when we define the benchmark. So then we can reuse this pipeline to improve our models. And the improvement can be done in different ways. It can, for example, the model can be retrained, or we decide for another algorithm and exchange the model, or you can use this heuristic as a fallback plan if something went really wrong. Right. The another point of the automation of machine learning CI/CD is, in general, the prerequisite for CI/CD pipeline is testing. So in particular, green tests. Machine learning testing is more evolved than traditional testing. So we will need to include, so we will need to provide tests for functional and non-functional requirements like robustness, interpretability, fairness, and so on. So this is also a huge topic, and a lot of going on here in research and in the industry. Right. The next point of the hierarchy of needs for machine learning engineering is versioning. This is also an important aspect and prerequisite for automation to streamline or shorten the cycle time of machine learning development. And versioning is used to trigger the CI/CD pipeline in our application, or it is especially if you are in the regulatory environment. So these are checkpoints for recovery, for traceability, and decision justification. Well, what we need to understand, and this is why I put the my second slide with 3 components of machine learning, is that that machine learning systems, 3 things need to be in sync every time: machine learning models, data, and code. And that means with new data will be produce new machine learning models, and probably some code changes will be required as well. So, and all the changes need to be versioned. Practically, we have a really good experience with DVC. DVC is a data version control. Is used for data versioning, for machine learning versioning. It can do much more stuff, or data ops engineers could learn this tool very quickly. This is probably why we had a good experience, well, and luckily we have Elle later these days, so she will do much better job in explaining data version control. So make sure you don't miss her talk. So let's go on to the 8th point of machine learning engineering principles, which is about design of machine learning software. So in order to, what we also need to understand here, that the life cycle of machine learning models and the life cycle of the base software might be different. So, and we probably don't want to rebuild the whole system just because machine learning, just because we renewed the machine learning model. So that means the machine learning models should be replaceable, and the software design for such quick changes or seamless changes is a loose coupling principle of software design. And depending on your architecture style or the architecture of your core system, be it monolithic or distributed, you might want to stick to different architecture styles. For example, if you have a monolith software system, you can use the microkernel architecture, which is flexible architecture style and contains two components: the core software systems and the business logic is distributed across the plug-in components. And such plug-in component can be or machine learning model, and the communication is point-to-point. And the core system usually have a registry where you can register your various components, and you can also use so you can replace the plugin or your machine learning model on runtime without the need to rebuild the whole system. Well, in the distributed environment, and this is the quite popular pattern, serving pattern for machine learning model, is a model as a service where we wrap the machine learning model as a web service and expose it through the REST API to the target application. And from the infrastructure point, we encapsulate all the technical stack of our machine learning model as a Docker container, and the Dockerization is de facto as a standard right now to expose or to serve or machine learning models. Well, so all that aspects that I mentioned before are somehow belong to the MLOps, which is the extension of DevOps to design, to train, to build machine learning based applications, and where we put machine learning model and data as a first class citizens. And there is a lot of noise right now about MLOps, and the amount of MLOps activities and amount of MLOps components will depend on the AI readiness, the maturity level of your company. So, and if you're just at the beginning, you might have just simple use cases for machine learning, and you might have manual deployment, and what we are going to do here in the tactical phase, we learn how to deal with machine learning. We learn this technology. We learn to fail on this, and if we have some use cases, we will deploy on an ad hoc basis. So we are just learning. So the next step will be a strategic phase where we utilize pipeline patterns. And use cases getting more serious. They are aligned on the business objectives, and we have specific workflows, and or models are exposed through the APIs, usually REST APIs, and in the last stage of the AI readiness is transformational phase, where we use fully automated processes, and we have already established patterns and best practices. We can innovate by using machine learning, and this is where we actually will use all the advanced machine learning practices like feature stores, versioning, CI/CD, continuous training, and so on and so on. So So that means don't get mad about all these MLOps hype right now. Applying machine learning or involving machine learning into the business is a process, and we just have to go step by step. Okay, the next point of our here is the hidden costs of machine learning engineering. And every software project will have a hidden costs. Machine learning project will have more hidden costs. And to be aware of all that costs, we use machine learning canvas again. And this is, as I said, I really like this framework because it forces you to think about stuff which is not obvious at the first time. So we will be forced to think about all that infrastructure costs. Can we have this? So if we have increased cloud computing time, so are we capable to pay for it? Or can we afford to include a human in the loop for labeling or for data cleaning? So one interesting point is, if we introduce machine learning, do we have people who will maintain it? So we saw already that post-deployment is as important as pre-deployment. So do we have skilled people to do this? And so on and so on. So this, all that hidden costs can we like iterate through these hidden costs during the initial step while filling this canvas. Good. The last but not least point. Every time we use machine learning, and if the predictions of machine learning influence decisions which will influence human lives or interact with humans, means we have a responsibility, and we have to be aware of all ethical issues of machine learning, of the application of machine learning during data collection or model training, and right now everyone is stating all that responsible AI principles. What I am missing right now is like a practical aspect of this. So, okay, I want to build a responsible AI, but how can I do this? And recently I discovered this framework, model cards for model reporting, because I'm convinced, and this is similar to the documentation for traditional software. We can achieve a lot of transparency in machine learning if we establish the documentation culture for machine learning development. And this framework, model cards, contains 9 sections, which also like a machine learning canvas guides you through the points which need to be documented. And in this way, we make our models transparent and describe describe all details, the use cases, all metrics, and describe the evaluation data and training data, so, and when you're forced to do this, then you automatically Right. So think about all that principles of responsible AI. The best thing about this model cards framework is there is a model cards toolkit, which you can install along with your project, like a pip install, and this toolkit will streamline and automate the documentation process of your models. It's very practical, so make sure you have a look at this. Well, so here we go. These are 10 principles of machine learning engineering. All of them are important, but some of them are really fundamental, and you probably don't need to worry about machine learning algorithm before you know that you don't have data, so you have to take care about that. Right, so I work at InnoQ, and we have at InnoQ a lot of stuff. For example, ml-ops.org is a website about the machine learning operations. If you like my sketches, you will probably like this site as well. Recently, many people really excited about the awesome MLOps. So make sure you don't spend much time there, but because there's a huge aggregator of everything about MLOps. But I can ensure that I look at every single link, at every single resource there. So this is a curated stuff. Well, so I think that's it. Thank you very much for your attention. So, and I'm curious about your take.
Yes, thank you very much. So I can definitely relate to everything you said, and especially like in many cases we don't need machine learning, so we shouldn't even bother with many different things. Like if we don't need, we just need to sit and think, is this the right tool? And often it's not. Also, I really liked your like this pyramid, rotated pyramid, when you said like the sort of stages of maturity for MLOps. Yeah, that was like you don't. It's okay. Like I think it was earlier. Yeah, this one. Like it's okay not to have feature stores or some other things. I think I can so totally relate to that. I just want to remind for those who are listening right now, if you want to ask a question, there is a link pinned to the chat conversation on YouTube. So if you click on this, you will go to Slido and you can ask Larysa a question. And we already have a few questions. So the first question maybe we'll start with. The question was, what is the name of the ML document format that you shared? It was, I think, in the point number 10. Yeah, this one.
So just Google for model cards for model reporting. This is a paper. This is a Google paper from Margaret Mitchell and Timnit Gebron. If you know these two names, you will be curious about. You will, if you Google for model cards toolkit, you will get the GitHub repository with all that instructions and examples.
Mm-hmm. Yeah, we will add all this link to the description later.
Sure.
Yes, so then Mark asks, when consulting others regarding such topics, what is the adoption and acceptance rate you generally see? If you can, of course, answer that. Maybe if you cannot disclose that, that is fine as well.
What I can say if the interesting point is this here. This is where I spent the majority of my time giving workshops exactly about this. And I can tell you the situation in Germany, and the point is people or companies are aware about these technologies, the AI, machine learning, and so on and so on. But and they probably understand the importance. But what I see, they don't know how to introduce it. And this is why we developed this method, where we go with event storming and try to identify use cases. So what I can say that it was my biggest surprise that many companies are still looking for use cases.
Okay.
So the readiness is there, but they don't know where.
Okay, so they want to use machine learning. They realize that this is important and this will give them strategic advantage, but they don't always know like how to start. And this is what they need help with getting started. And this is where this canvas comes into play, right? So you can use it to actually brainstorm and identify.
Exactly. But first is to identify the opportunity. So and the using Canvas to structure, to dig deeper, and to understand every single like here. So every the translation between value proposition and prediction task. So you are doing all this here, and right. So and so there is not much methods and practical. Right, practical guides how to do this. Like if we and if you don't have experience, so if you don't create any machine learning models, it's very difficult to find a starting point.
And you also mentioned at some point CRISP ML, right? So it was. Okay, I'm just curious, what is the difference between CRISP ML and CRISP DM? Like CRISP DM is like, I don't know, 20 years old, right? This cross-industry standard process for data mining. Right. And then some people, I think they decide, okay, data mining is old, like probably it needs updating, and they came up with this CRISP ML. What is the major difference between these two?
So basically, right. So the ideas of CRISP ML is quite similar to DM to data mining, but the emphasis is on data quality. On model quality, the quality assurance of machine learning models. So they emphasize that there's a lot of testing, machine learning specific testing, which need to be involved into the complete process for deployment, and this is actually the huge or the main difference between these two. But if you know CRISP DM, you will also get well with CRISP ML.
Is it something you often use?
I structure as I see these phases, and I try to go through these phases and structure the projects along these phases. So definitely, so we don't skip the business and data understanding.
This is where canvases also help.
Exactly. So and this was so important. And actually, I think this very useful paper in general. So it was the collaboration between TU Berlin and the automotive industry here in Germany. So this is actually one of the paper which actually reflects the real data machine learning life cycle, project life cycle.
Yeah, I didn't know it was coming from the Technical University of Berlin.
Klaus Robert Müller.
Oh, okay, of course. Okay, so we have a couple of more questions. John is asking, if you're joining a team with existing machine learning product, but without MLOps, which practice is best to start with while still delivering value?
So you have machine learning, but you don't have machine learning operational practices. I would think that first I would start with versioning in order, because the versioning will be versioning and testing. So you probably will need to establish these two practices, because the next step will be triggering your CI/CD pipeline to the all that steps automatically. Yeah, versioning, testing, continuous integration, continuous delivery.
Yeah, and by the way, talking about MLOps, so you mentioned the team, and there was MLOps the engineer, then there was a DevOps engineer, and then there was IT Ops. I'm curious, like why do we need three different people, three different operation engineers, or this can be one person?
When okay, the first thing is this picture probably is a little bit idealistic picture, right? So this picture picks not person, not people, but roles. And I think depending on the scale of your organization, you might or you might not need these roles, and you will go well with just with DevOps engineers. And I have to so just because I took this picture from a book, so this is why it's here. So I reference this book. But you're absolutely right. So it depends on the scale of your organization, and so there won't be so many organizations which will be on that big scale.
So we have still one more question. Ismail is asking, in your machine learning deployment decaying slide, how can we be sure about the success and improvements in terms of performance for a new model?
Yeah, so like I told, we monitor machine learning performance, and especially if we are lucky, we can if we have labels, so we can identify the drops. So we will need to establish the monitoring for machine learning specific parts like or metrics like F measure. So we are monitoring the F measure of machine learning model. But as I told, we might not have the access of to labels at the real time. But what we can monitor is the distribution of input values and the output values. So, and if we identify the shift of two distributions, like the train data distribution and the real life data distribution, this might be trigger for alerting that something is going wrong here.
Yes, thank you. So Mikio is already, he already wrote me that he is ready to join the call. So yeah, thank you very much for for joining us today and for sharing all this useful and valuable information. And yeah, and I really like the style of your slides. So this is very nice, like with this personal touch of drawing everything. Yeah, so thanks a lot. Thanks for joining. And yeah, Mikio, if you're listening right now, this is a good time to join.
Good. Thank you very much for having me. See you around.
Yes, goodbye. Yes, so now we are waiting when Mikio joins, and we will have a short couple of minutes break. Hello.
Yeah.
Hey.
Good to see you again.
Yes, likewise.
So these seems to be quite popular.
Are you watching it on YouTube?
Yeah, I watched the last 20 minutes.
Okay.
But I get like 70 people or something in there.
That's yes, it's right bad, now 70 people. Also, like I'm also watching it. It's on my phone, so it's like 69.
Okay. Yes.
So we will have now a short break. So yeah, maybe we can quickly check that you can like sharing slides work.
Yeah, let's see.
And then maybe just 1 or 2 minutes of.
So
great.
I tried this already this morning. Does it work? Yeah.
Yeah, it does. So yeah, maybe just I need a small break, and then maybe also the audience who is watching also need to take a small break. So yeah, let's start in 2 minutes.
Yeah, I'm here. See you in a bit.
Yes.
Getting ready.
Okay. Is it a picture of Berlin on your background?
Yes.
Okay. I think I recognize it. Is it in near Alexanderplatz or something else?
Oh no, it's in Friedenau. This is the small, like 2-kilometer autobahn down to Steglitz, to the
Okay.
So that's right from where I live.
I don't think I
live
there.
Sort of, I think up here, no, up there, and then a bit around the corner.
Okay. Yeah. So I think we're ready to start.
Okay.
Yeah, just before you start, I just wanted to remind that if at any moment or during the presentation you want to ask a question, there is a pinned message in live chat in YouTube. So just click on this link and you can ask Mikio any question.
Okay, but I won't see it, right? Because
I will just read the questions to you after the presentation.
Good. Yeah. Okay.
Yeah, please, the floor is yours.
Yeah, already live. Very good. Hello. Yes, thank you very much for joining me. My name is Mikio Braun. I'm currently working as a consultant, helping companies getting better with machine learning. And previously, I worked at Get Your Guide and Zalando, both as a engineer manager for data science teams and as a principal. And today I want to talk about putting data science in production, and especially I want to talk about the tool, the tooling landscape. So, yeah, right. So if you so here I collect. So these aren't even all the logos that I'm talking about in the talk, right? But as you know, so every time you check, there are more and more tools that either promise that they're useful for machine learning, right? Or people tell them, "Oh, have you worked with this? Have you worked with that?" And it's just so much, right? And in this talk, what I'm trying to do is to give a bit of order to all of this, so that you maybe can also have a better idea of what's out there and what the different tools are and what you want to look into. And sort of the way I want to organize this is by starting something that potentially every data scientist knows, because this is how you start, right? So there's sort of this core of machine learning workflow, which you do whenever you start machine learning. That's how you do. That's how you start. So it's usually quite simple. So you have some data, which is just on the file system. So it's just a file, right? You load the file, you do something with the file, and then you train a model. You look at the errors, and then maybe you tune it a little bit with the parameters till it looks good, different kinds of pre-processings, and then you have the model. And then you might save the model, or you just keep it in memory, and then you apply it on some data to get the results, right? And this is sort of the very core. So this is what you sort of do. At least whenever you do machine learning, there's some version of this that's happening. And so by now there's a pretty standard set of tools also using. So I think over the years that's converged very much to Python. So there used to be also, like in the days when I was still at university, we were using MATLAB, right? But then MATLAB is very expensive. So nowadays everybody's using Python or R, but I think for like data science applications in industry, most people use Python. And then there are libraries. So Jupyter has sort of replaced the normal IDE and console, because it's like a nice mix of the two things. There are libraries like scikit-learn, which has all the standard machine learning libraries. And then use something like matplotlib for the visualization, and often you use pandas to just load the metadata and do the pre-processing, right? So that's all good. And the question is, so what? Like in a way, that's really the core of machine learning. So, but what else do we need to add here, and why this? What does in production even mean, right? And typically, when you want to put something in production, you have to deal with a couple of challenges. So, for example, you want to use much more data. Yeah, so you want to, I don't know. So I've worked, for example, in Zalando on the recommendation team. As you can imagine, Zalando, they have like millions of visitors, millions of customers. So that's a lot of data. So that's probably not something you can just do like load from the file system. So the data isn't even in the file system, right? The data is somewhere in the cloud. You might also want to use more advanced models than what scikit-learn has, but you don't want to sort of spend a lot of time re-implementing papers. And then, so all this, what you do, this sort of getting the data, playing around with the parameters, trying out different things. So the more sort of industrial it gets, right? The more you also want to have some workflow support, because usually you're in a team of several people, and you want some documentation about things that you've tried, so that you don't do it again, right? So you want to remember what happened. And then, so like in this core machine learning, right, you have the model, and then you can apply it to data. But there are many use cases where actually what you really want is real-time predictions. So you want to have the model somewhere in your system, and then you can ask the model something and get something back. So for example, again, for recommendation, right, whenever there's a page loaded, you want to grab some data for the customers and context, and then you want to know what are the best recommendations for this. So, and that means, so machine learning really has to become part of your technical infrastructure. And finally, the last point is automation. So all these steps that you did manually, in production, often if you have changing data, what you actually need to do is you need to retrain the models like once a day, once a month, keep them up to date, and that brings a lot of other challenges with it. Okay, and what I'm going to do in this talk is sort of keep the original core module, like this core flow in mind, and then go through these different topics here and talk about like what kinds of tools are there and how could they help. Yeah. So I didn't really, sorry, I'm not doing it in the order I wrote it here. So let's start with more complex models. And I think this is still what's still very easy, or which you might even have looked into it, right? So there are lots of libraries out there like GBM, XGBoost, which are just more and which give you more machine learning algorithms, so you don't have to implement them. Then there are libraries like PyMC3 for Bayesian modeling, time series forecasts. And then, of course, there's this whole deep learning stack, so PyTorch and TensorFlow. And then there's this new thing called JAX, which is like an automatic differentiation layer on top of NumPy. And using that, you can actually create quite complex models and then also train them automatically. And finally, there are projects like Hugging Face, which actually are like a huge collection of pre-trained models that people have created and loaded up somewhere, right? So this is something, so there's this big set of tools that you can look into, and they become bigger and bigger every month, it seems, right? And why do you need them? So you don't want to do this low-level code in NumPy, right? You don't want to implement numerical algorithms. You also don't want to deal with how to parallelize things on the GPU or write your automatic differentiation code and so on, right? So this is, I think, one big area, and this is all stuff that's used in production, right? So at Zalando, for example, one topic we worked on while I was there was having more and more personalized models, and then one thing we looked into, for example, was using TensorFlow and recurrent neural networks to really track the actions of a customer and then have a prediction that is both personalized and takes like the recent actions into account. Okay. Workflow support. So this is an area, I think, which is not as well as mature as the algorithms, right? So we're getting like a bit further away. And this is really about like tracking data, experiments, workbooks, and so on. And you might, as I said, just do it for yourself, or you also have to do it in a team, right? And then there are, for example, libraries like DVC or tools, which is sort of version management, but for your data, so that whenever you have a different iteration, you later on still know actually what data it was that you used during the experiment, and you can track that, right? So if you don't do that, what often happens is you have many versions, and you overwrite data, and then later on you don't really know like which version of the data belonged to code, and you cannot reproduce the results that you had. MLflow is also a tool which is sort of within the Databricks ecosystem that is also exactly for that. So you can have models. It's like a database where you have different runs, and you can evaluate it, and you get a table where you can sort of look at what worked and what had which performance and didn't. And then the icon in the middle, that's the sort of the group icon for SageMaker, right? So SageMaker from AWS, when they started with it like 2 years ago, it was essentially like a notebook server, and then some libraries which made it easy to train, to spin up training instances or deploy models. But since then, it has become much larger. So now they're covering all kinds of things. And then there's also some version of this in here. So this is something you should definitely look into if you want to get better at documenting and tracking what you did. And you can, of course, always have, or usually you will have some version of that built yourself. But then there are also tools you can look into here. Okay, so if you have any questions, of course, you can write them. And then Alexei read them to me. So now we come to the another area, and that is sort of the scaling out. That was the first on my list. So usually when you go into production, right, so even if you have a very beefy machine, there's just a limit of the data you can hold. And also in production, what often happens is that the data is somewhere else, right? It's in some database, like tracking data is collected somewhere on the cloud. And sort of what was just your file system in the original case suddenly can become something very complicated. So this bucket here, that's the official Amazon AWS icon for the S3, right? Which is, I think, so there are things like that also for Azure and Google Cloud, but they have some version which is almost like a file system. So you can essentially just have lots and lots of data somewhere, but it's very flat. There's no support for any complex access or querying, right? But it's good enough. So you have a library in Python that allows you to access and load this data as if or stream that data in the best case, of course, too, and as if it's just a local file system. And then, especially for this pre-processing part, there are many tools which essentially feel a bit like SQL, right? So it's not really a SQL database, but they come with a query language that looks almost exactly like SQL. And it has turned out that's a very good abstraction level for doing a lot of the pre-processing that you actually need, right? So Spark, for example, Apache Spark originally came more from this MapReduce kind of parallelization method, so inspired by Hadoop. But then over the years, they realized, so writing like map and reduce jobs is quite complicated, but you can actually have like a SQL engine on top of that uses this engine and parallelizes in a nice way. And I think nowadays, when you use Spark, usually you just treat it as a SQL engine to do, right? And then you can do all kinds of, so you can transform data, you can compute statistics on your data. They also usually have some version of doing aggregate statistics over time windows and so on. And so usually you'll be finding that you use that quite a lot if you deal with like really huge amounts of data. So that's also sort of the pre-processing part. When it comes later on, for example, hyperparameter tuning, that's an area which can also be very easily parallelized because you just have like independent training sessions per parameter set. And then there are newer libraries like Ray or Dask, which allow you to scale that up easily, right? Then of course, so the GPU training, TensorFlow has also some support for making that faster or even doing multiple CPU. And so on, right? And I think so this is maybe like the one of the things you will want to learn whenever you have to deal with a lot of data, and it's so, but it's actually, so the SQL layer, I think, or that abstraction, or what I like about SQL is that it's so old, right? They really figured out a way to make it very smooth, like from the interface, so it somehow makes a lot of sense. Okay. Yeah. So next, let's come to automation. As I said, so usually when you like there are some applications where you have some data and you want to train it, and then that's it, and then the model is good for quite a while. But if you're training on real data, then there are usually often some drifts in the data, or the data changes over time and so on. So what you want to do is you want to automate the whole training, right? And maybe even the redeployment. So at Zalando in this recommendation team, right? So once per day, they would just run the pipeline and then also redeploy the model if everything looks good. And some companies, so I think Netflix, they even push this so far that as part of the automation, you even do an A/B test. And if the A/B test is good, then they automatically deploy. And if not, they roll back, right? So that's how far you can go. And actually, so I think if you're sort of used more this local data science, this core workflow, what I've seen in the past in my experience is that it's quite a surprise that you do this thing once, maybe you work on it for a few months, like manually tuning it to a point where it's very good. And then when you say, okay, now let's put it into production, then you have to automate all of that, right? All these manual changes that you did, all these manual decisions have to be put in a way that you can just run it, and then it produces good results, which can be quite a challenge. So you should have that in mind, right? And besides that, so there are many tools out there that allow you to schedule these whatever it is that you have. So the most prominent of that is Airflow, which has been developed at Airbnb originally. So it's using Python code essentially to define pipelines, and then you can run them. And what most of these tools, all of these tools support, is not just like running one task, but actually running like a pipeline. So actually like a DAG, a graph of tasks, which all depend on one another. And then they figure out, okay, what is the best way to run it also in a parallel fashion, right? Which can be very useful. So these can really get quite large. So I've seen teams which sort of, they have like one pipeline for basic features and then another job that picks up on those, and then it branches out. So you can have something that takes, I don't know, 10 steps, and then you do that for all kinds of, so it can get quite complicated, right? And eventually, so this is something you will have to look into. There are more challenges, which I think are not yet covered very well by tools, as I said. So like model drift or detecting data quality issues, right? So the one thing is, as I said, you run the code, but the other, so a lot can go wrong. So maybe you know, some data source has a bug and the data doesn't look like it used to have, and then you're trying to automate it, and then you but the code still runs through, right? So you have to do a lot of checks in there, and there are some ideas how you could automate that stuff as well. For example, using some statistics with your data to figure out whether the data changed significantly, and then getting some other automatic error messages, or maybe stopping the pipeline. But there isn't too much yet. So that's still an area where you have to invest some brain power of yourself. Okay. So now, like it's finally come to this real-time application, right? So like in the core flow, as I said, maybe you have the model, you do something with it, you apply it on some data, and then you have the results. But sometimes you really want to be able to get like one prediction at a time. And that usually means nowadays that you package the model, you put it behind a REST API, right? So, and then you can do HTTP requests to compute the model. And so we take a few slides to talk. This is a very complex topic, I think, or so let's talk about a few of these aspects. So usually what you do is you take a web framework like Flask for Python, which makes it quite easy to add an HTTP layer around your functions. Right, but then so the question is, how do you deploy it? And by now, the standard has become that you Dockerize your application. So Docker is like a whole Linux configuration, but which is will not run in its OVM. And then you run the Docker. You deploy it on Kubernetes or directly on an instance in the cloud. And I think so. These are actually quite complicated technologies, but at least sort of how to turn your model into something that is within a Docker container. That's something that you need to know, I think. And then maybe there's somebody who can help you with all the rest. I should also mention that in some cases, people sometimes believe that they need the real-time prediction, right? But in some cases, you don't actually have to deploy your model, but you could still in batch compute all the predictions and then put these predictions in a database, and then you just get the predictions from the database. So, for example, if the objects that you want, you can have predictions on are bounded, right? So coming back to recommendations. So what you can do, and what we also actually did, is to pre-compute the top recommendations for all the articles, and then you put these in the database, and you just query that, right? And that can solve a lot of complexity, because right, you don't have to think about like how fast it is or any of that. And putting a database access behind a REST interface, it's something that's quite easy and well understood. Yeah. So if you still want to do it, right, there's a few things you need to consider. And one is, so depending on your model might actually depend on features that you computed from your data, right? So you have some articles, and then you do it in this pre-processing step, you transform the data. and then you trained your model on. And now if you want to do real-time predictions, right, so you need to potentially compute these features on the, or you need to have the features when you want to do the prediction, because the model only understands, I mean, the model is sort of built on this feature space and not on the original data space. So the question is, so where do you get these features from? And one way to do it is to sort of, you take the features after training and then you put them in a database, as you can see here in the picture. And then at prediction time, when you want a prediction do for a certain item, you go to this database and pick up the features that you've pre-computed during training, and then you do the prediction based on that. Right? And often what people, for example, use is not like a full SQL database, but a key value store like Redis, which is mostly memory. It's very fast and has a simpler data model, and is good enough for that. Right? So and one problem here is, of course, that you only have features for the items which you've seen during training time. So what do you do if there are new articles coming in over the day or new users and you don't have features for those? So how do you do it? And the one way to do it, or there's an architecture to do it, which looks a bit like that. So it tries to have sort of the pre-processing step. That's these yellow pre-processing box here, right? And these pre-processing box actually works on streaming data. And so it means you can apply this pre-processing step both to real-time data as it comes in, but as well to batch data that you have. And then you can sort of use the same feature computation mechanism in training, but also have it run on your data as it comes in. And then after training, these features get stored again in this feature store database, which could be again Redis or Cassandra, maybe another key value store. But you also have the streaming data come in. And then you have sort of always up-to-date live features for your model. Right. The one problem here is, of course, that you need to be able to compute these things in real time. If you cannot do it, right, then maybe you have quicker jobs or smaller jobs that recompute features for new items after the model has been deployed. And so once you get into this whole real-time data processing, you will get to know systems like Kafka or Pulsar, which are essentially message buses, but they also have ways of running like a streaming SQL query on the data that then also allows you to do some processing there. Right, but that's sort of, so I think if you get to that stage, then you might have some machine learning engineer or a backend engineer in your team who will take care of that, because that's like, if you think about where we started, right, this is already very far away. Okay, so and lastly, so once you go into this whole production area, then you also start getting, so the problem is, so once your system is in production, right, you will start to get in contact with engineering requirements, right? So the things have to be like stable, you have to monitor them, they have to be fast enough, you have to think about auto-scaling and so on, and then you get in contact with even more tools, right? So for example, if you used to work on Jupyter notebooks most of the time, once you go to production, you will want to have stuff in GitHub or Git or some other version control system, because in production, you really want to know, like, if something is in production, you need to fix it. So we need to figure out what software exactly is in production and so on. For this monitoring, there are many tools like Grafana, it's an open source tool, or Datadog or Splunk, which collects all the metrics from the system, and then you can look at these plots which show different metrics like memory usage and so on. There are actually, like in TensorFlow and in SageMaker, they also have some some tools which support deploying these things and also collecting some metrics themselves. So you might not have to build this yourself. There's one startup on Spectre, which takes your deep learning model and then optimizes it for prediction time on whatever hardware you have. Right? So very often you do the training on the GPU, but once you go to prediction, you actually don't want to do it on the GPU, but on the CPU, and that's a lot slower, right? And what on Spectre does is also optimizing it for the different CPU architectures and so on. Yes. Okay. Yeah, and so this the last area I wanted to talk about. So coming back to this original data. So like we said, the data is then in like in some S3 bucket or maybe some database. But the question is also, how does the data come in there? How does it get in there? And for that, there are by now like lots of libraries or actually platforms like Databricks or Snowflake, which are like the modern version of a data warehouse, which are used in many companies to collect all the different data and make it available. And then usually have some kind of SQL engine on top of that. And then another topic is, or another class of tools, I think, which will also be much more relevant in the future, is how to generate labeled data for your data sets. So for some data, like if you're using click data, it's sort of implicitly labeled because you know like what the customer did and then how they behaved afterwards, so you can structure labels from there. But if you're working on text classification, for example, for analyzing customer requests or something, right? Sometimes you just need to be able to, or you have to create lots of labeled data to train your models. And by now there are a few startups around this, quite successful startups, which help you with that. So you can sort of outsource the whole labeling process to them. So the original one was Amazon Mechanical Turk, which, so actually they paid people to label data points. Another one is scale.com. And then there's another one called superai.com, which sort of even takes into account the model training. And then they don't just outsource the label giving, but they also provide some kind of performance guarantees, right? So they show the same label to several people to get confidences and so on. Yeah, so I think, yeah, that's so right from where we started, we're now really far out, like how does the data come in, how do we get the labeling? And that was my, that sort of concludes also my tour. Now, if you look back at the labels, at the logos we had originally, I tried to make this little like tooling landscape. You've probably seen things like that, which are much prettier. So I need to work on this a bit more till the spacing between the boxes is fine or not. But now, so hopefully you see like there are all these different, so you see a bit more structure in all the tools that exist and also how they fit into the different use cases that you need. Right, and then the full system in the end looks a bit like that. So you have the customer on the left-hand side, data ends up in a database and logs, you do the data extraction, and then the actual machine learning comes, you have the model, and then it goes over into production with all the monitoring, and that produces the result to the customer, and then on the bottom of it, you have all this automation. Right? So machine learning, unfortunately, so once you put it into production, it's really just a small part of the overall system. Yeah, and I think so right now, I would also say it's not really clear like what the best way. So there are lots of tools that tackle different parts of it, and some are quite mature and some are not quite mature, which also can make it quite difficult to figure out what is what. Okay, so yeah, what is the summary? So I think like there has been a lot of movement in that area over the few years. But obviously, so if you start as a data scientist, or depending on where you are, right, so it feels like can feel very overwhelming because there are so many tools to learn. But I hope so with this like categorization that I gave, maybe you know better where to start. It's very hard to keep track, I think. So just to pick one example, this ML flow. So when I first heard of it, like 3 years ago, right, it looked like super simple. So it was a bit like, okay, I don't know, I have done versions of this when I was a PhD student myself at least 3 times. But since then, I mean, these are really big companies that put a lot of money and effort into these things became quite good. And yeah, but that's really hard to know, right? So you have to be constantly checking to know what's happening. I think, which is also not surprising, but many of the tools actually don't cover all different use cases for machine learning, but they start with the simple ones. But on the other hand, like in the marketing, they often promise that they are like the premier machine learning platform that will solve all your needs. So it might sometimes be really hard to figure out whether what you want to do fits in the case or not. Another observation that I made is, so right now I think it feels a lot like devs, they're trying to copy DevOps, what they've learned there, and data engineering, and then put that into machine learning, right? So they even can call it MLOps. And sometimes I have the impression that so stuff is just copied a bit too quickly or by people who don't really understand the needs of machine learning people, right? So for example, I think in many of the tools, they often try to build everything into notebooks, which is nice on the one hand, but I think, at least what I've seen in companies is that the notebooks are good for one part, but if you go into production, you have to move over to more rigorous source code tracking and things like that. But many of the tools don't have good integration for that. Oh yeah, that's the next point. Right, so I think this is really important also because for me, a big unsolved problem is, so you start in a notebook and you have something that works, and then you clean up the code, you put it in a GitHub project, you deploy that. But then, of course, what you want to do after that is go back to the original exploration and figure out how to improve it, right? But how do you do that? It's not, so people I talk to say, so some say I just copy and paste the code, put it back in the notebook, work on it, and then I do it again. So it's like a lot of manual copying back and forth. Yeah, other people start doing a lot of work really in the Python project, but that's also slower. So I think there might be some piece missing. Okay, and finally, so I've started to collect some of my writing into something which is, let's see whether it really will be a book or not, but there's a work in progress on book.mlpractice.com. And just check back and see like what's being added there over time. Yeah, that's it. Thank you very much.
Yes, thank you. So what PHAI, the square that you have, and what is that?
That's my secret new branding, which is which is not yet.
Okay. Okay, yeah, we do have a couple of questions, and I want to remind you, if you want to ask Mikio a question, you go to live chat and there is a pinned message, and you just click on the link and you can ask Mikio any question. And there is one question from me. Like if you go a couple of slides back with like all these tools put together and then squares around them. Yeah, this one exactly. I see that like, let's say you want to start a project, right? And then you see like there are so many tools, like you have Dask, you have Ray, you have Spark, and then you have, I don't know, Luigi, Airflow, then you have Snowflake and BigQuery. And then just making a decision which tool to use, like, because there are so many. And I think what you have here is just 1% of the available tools, right? There are a lot more. How to choose the right tool for a particular problem? Maybe do you have some sort of maybe a rule of thumb or some recommendation?
Yeah, it's a very good question. No, I think so one is, of course, you should start with the tools that you already know, right? And I think also whenever you start a project, it's also okay to sort of get a sample of the data, just copy it somewhere locally and then start using that. Yeah, so that's true. I think that's always good. But then on the other hand, so one problem is also that you need to start thinking about how you want to, like how you need to deploy it later on at some point, because otherwise you might build something and then figure out, oh, it doesn't scale at all, right? So that's always the challenge. In general, when it comes to machine learning projects, I think it's always important to think about, okay, what is the biggest unknown? What is the biggest risk? And then start with that. So you can, right? So otherwise, so you could be like designing a very sophisticated software architecture, but then figure out that the data is super noisy and you cannot support the use case that you have, right? So it's always good to start with that.
Yeah, but even there are things like this Kafka and Pulsar, right? They're quite. I haven't used Pulsar, but I think they're doing pretty much the same job, right?
Yeah.
Like just selecting the right tool. Let's say I don't know Kafka and I don't know Pulsar. How do I choose them? Do I look at number of stars on GitHub, or there's
Yes. Yeah, I think with Kafka or Pulsar, so they're really, I think from the feature set, they're very similar. So from architectures or what I've heard, they're a bit different. I mean, with these, it's probably usually that your engineering organization already decided what they have in use, right? So most companies that I know are using Kafka, not so many using Pulsar. Yeah. Yes. Nah, I don't know. So
so basically, like first take the tool that you know. If you don't know, like take the tool that the organization uses, and then maybe the first like look at the number of stars in GitHub or something.
Yes.
Or maybe your friend knows something. And then
yeah. I mean, what I always wanted to do, that's maybe hopefully enough time for that, is to come up with like a few use cases, like a very simple one, which is just like you learn something, you predict something, that's it. And then maybe forecasting, something with time series, and then sort of have different use cases which become more and more complex. And then actually for each of those, really look at, okay, SageMaker. So they promise so much, but can I really use it for that, right? And then I think that, yeah, but I agree. It's so the problem is, of course, also you cannot just try these things out, right? So if you, I don't know, if you say, okay, let's try Kafka and something else, could easily be like a few months that you waste on that. Yeah, so this is, I mean, this is also, I think, what I hope to be providing to my clients. So some insights based on what I've seen. Yeah.
Okay. And there is a related question. Is there a standard technical stuff that that is most commonly used to tackle machine learning problems?
No, not really, I think, right? I mean, so what I see or hear a lot is so scikit-learn. I mean, what you see here, scikit-learn, like GBM, XGBoost, many people are just using that. So Jupyter, of course, everybody's using Jupyter. Some people are using Zeppelin, but Jupyter, I think the infrastructure is much better. I think most industry applications use TensorFlow. And then sort of doing with like in Flask, putting your model in Flask and then into Docker. So there, even if you look at the SageMaker documentation, so there's something like an implicit standard how to organize it so that you can deploy. So there's already like what are the entry points, what are the files that you have. You can use that. And then, I mean, some of the things are newer, like Apache Ray, right, which is a bit like a multi-processing engine on top of Python. I think they started like a few years, maybe 1 or 2. So it's not that you knew yet. So I think if you only would use it if it has you have a very special use case where you need it. Yeah. And then
So do you have any recommendation on the most important tools? I guess you kind of just said that. Yeah, but maybe some like maybe let's say you start a project, you personally, and you're not restricted by any of the tech stack. Let's say, what would you use for the cloud provider? What would you use for serving and for things like that?
Okay, yeah. I mostly work with AWS, so I think I would, and SageMaker, as I said, has grown really a lot. So I would probably start looking into that. But also, I know that I think for Google Cloud and Azure, they have similar things, which are, I think it's more important sort of to really have an idea like what you need and then start looking into whether it makes sense or not. It's really hard to tell from the, I mean, so in general, I always think it's good if you start with some more classical method, so random forests or logistic regression. I mean, unless you really have a use case like computer vision where you need a more complex model. And then, as I said, so having like a small data set, see that works well. I think the real question is also really, so how, like what are the requirements for serving? Do you really need to have it real time? Is it batch? Is the domain restricted so you don't even have to deploy it? You could just put it in a database, and so on. I mean, many of the tools are also not, I think not super user friendly. So Airflow, like I've seen, if you have that running for a few years, it gets very complicated. Like it's just like the pipelines have become really huge. So you can spend a lot of time on that.
Yeah, so basically there is no single silver bullet. You always, like, the answer is basically depends, right?
Yes,
So you look at the
unfortunately, yes.
requirements and then,
Yeah.
but yeah, maybe SageMaker is kind of close to that, at least when it comes to training, and well, they cover a very broad range of things there, right?
Yeah, and it's like every few months it expands. Yeah, I mean, I think for what's for Google Cloud, right? So because TensorFlow is also from Google, I think that's probably integrated very well. Yeah.
Okay, then we have a question about Presta. Where would AWS Athena Presta fit best in the workflow you described, and which tools from your list would compete with this?
I think so. This is for like you would use it in the pre-processing stage, right? Because it's also these essentially SQL engines which would run on a 3 buckets or so, sort of unstructured data. So I think it's close to Apache Spark. So I've seen, yeah. So they would be in this parallel compute bucket, I would think here.
And perhaps also like similar to BigQuery. So they can
where's BigQuery? Oh yeah, down there. Yes. Yeah. So I think this you could also argue whether these categories are the right thing or move stuff around. Yeah. But I mean, so the big advantage of something like Athena is it's serverless, so you don't have to write it. So if you have Apache, if you have Spark, either you need to spin up your own cluster or your own Databricks. And yeah.
And so, Athena is like BigQuery. You just write a query, you hit the run button, and then you just get the results.
Yes.
Right? Yeah. Do you have any recommendations about AutoML tools?
Oh, okay. Yeah, I'm not sure whether they already are good enough that you could just use them. Or I think the problem with AutoML tools is always that the use. So who is the user? Is it really people who have no idea what they're doing, right? Then, but then I think I think we're not quite there at the point where you can really trust that people don't misuse it. And then otherwise you probably have your own ideas how you want to do it, right? Yeah. So I would keep an eye on it, but probably not still rely on it for production use cases.
Yeah, because maybe you heard about this, like Google's AutoML did pretty well in a couple of Kaggle competitions.
Yeah.
Yeah, that's Kaggle competitions, right? It's not like you
I mean,
have to have data prepared.
Yeah, I mean that's another part which I haven't covered in the talk at all. But so if you're in production, usually means you're in some company, and then there's this whole other area of like how data science fits to the product development, right? Because so usually it's quite unusual, I think, that you have like a well-defined problem and you get some data and you have like a very clear defined machine learning task. But often it's more like, we have coming back to the recommendation. So we have it, people don't, so we want to raise the click-through on the recommendation box by 10%. And then like there's a lot more that you have to do before you get to the point where you could hit the run button. So, and I think that's something that AutoML cannot use it yet. Solve. Yeah. But I mean, if it got good enough, then maybe you can spend more time working with your product people.
Yeah. Having all these tools, like knowing all these tools, and like it's not really possible for a single person, right? So is this something like can you see all of them in one job description, or they probably more fit for a small team?
Yes. Yeah. I think you wouldn't. I think you wouldn't, unless you want to be like a one-man startup, then maybe you need to be able to do all these. But well, I think so. For example, Grafana, all that like there's all these data warehousing tools. That's usually completely different people who work on that. It's maybe for if you have Grafana, then you need to think about how to put the metrics in there, how to set up alerts or something. But you don't have to do it. And I think there's also this, what was also in the last talk, right? So there's like the split between data scientists and machine learning engineers. So people who really know all about these tools and then can help you with the details here, always how to put it into production. So you would more use it from the data science side, and then they would pick it up and make it performant and see that it's properly packaged and everything. Yeah. So I think for data, so I think as a data scientist, or what I've also seen is, so for example, you spend quite some time in Airflow building on your things, you spend quite some time in BigQuery or one of these things, working with SQL statements to get the right data. So you have to have some working knowledge of a lot of them, but of course not like you're user of these systems, but you don't have to set up or maintain the whole systems.
Mm-hmm. So basically, working knowledge is somebody set the system up for you, like somebody set up a Kubernetes cluster, and then you just know how create the deployment in this Kubernetes cluster, right? You don't need to know how to operate it, how to maintain it, how to do all these things.
Yeah.
And so probably like from all these tools, there may be like for 3, 5, 4, 5 people, maybe like we have like machine learning engineer, data engineer, data scientist, right? Perhaps also like some sort of platform engineer or DevOps engineer.
Yeah.
Yes.
Like
a big chunk of like they're overlapping a bit, but not completely. So it's unreasonable to expect knowledge of all these things in one person.
Yes, because I also don't know all these tools, right? So, but I think it's also important that you have maybe something like this in your mind, right? That you can quickly know, like, okay, this is more like that, this is more like this, and then maybe know like a little bit of detail, like what is the difference between Spark and Ray, or like as we said, so Spark and Athena, and that already, enough to make some decisions, like when to use what. Yeah.
Yes. Then we have a related project, and maybe I have answered that accidentally without knowing that this question is there, but maybe you now have a chance to give your answer. What is the ideal, smallest or leanest team in terms of job roles that would cover all these different workflows end to end?
It depends on I think, so you can have like one data scientist initially, right? And then they could cover this whole workflow. But then I think, other people need to, but then somebody needs to set up all the other, so some data engineers who are doing all the other things, right? So, I mean, it depends. So usually you don't start like in a vacuum, right? So there's already some infrastructure in place and some data engineering. On the other hand, I think that's like a big complaint, right? Which you often hear from data scientists. So you think when you start on a project, you think you're doing data science, but then for the first month or so, you're just collecting data sources and doing work like that.
And which means that the company shouldn't have hired a data scientist in the first place. First, like they should have hired maybe a data engineer, like you said. Like usually it's not something in vacuum, so there has to be something. Then having a data engineer helps. And then data scientist, and then somebody who sets up the tools like all these Kubernetes and whatever, right? So that would be the minimum team.
Yes. Yeah. I mean, so you don't have to. You can also. You could only really need Kubernetes if you just want to deploy one thing. I mean, actually, for that, I think things like SageMaker are pretty great, right? Because you can just or in general on AWS, what's interesting is they go more and more into this serverless thing. So you just have services where you can do something, but you don't have to maintain infrastructure. So, yeah.
Okay. What is your favorite tool and the favorite platform that you go to?
Favorite tool?
Or tools, actually, like I didn't read it correctly. It's plural. Personal favorite tools and platforms that you go to.
Yeah, no, I think doing the core, like Python, Jupyter, these like the upper left visualization, that works well. Yeah, I think Docker is also is really nice once you understand how you do it, right? So you essentially, it's a bit like a shell script of the things you would install if you have a new machine, and that's it. So that works well. Spark is pretty nice. So it's actually also quite powerful. If you once you go beyond the SQL layer, you can also do quite interesting stuff. So I also did a lot of coding in Scala, and then once you do that, I think Spark can actually be quite nice. Yeah, I'm not really a big fan of Airflow, just because every time I see it, it's quite messy when you use it. So with Cassandra, I've had some stories. It's operationally pretty expensive. So I had a team that just did Cassandra migrations for months. So it's like 2 people just working on moving it from one data center to the other. Okay, while it was still online, that was maybe why it was so difficult. Yeah, yeah, yes.
That wasn't your favorite tool, I guess, Cassandra.
No.
Okay. So what are the different patterns of deployment models? So you covered already deploying it as a REST endpoint, or maybe it was Larysa actually in the previous talk. What are the other ways of deploying models?
Okay, yeah. Yeah, one is, as I said, so I think like the simplest is just batch. So you just you don't deploy it at all, and you just have the results, and then these end up somewhere. The next would be that you sort of do batch predictions, but you put it in a database, so you also don't really deploy the model. And when it comes to model deployment, I think the question is also whether you really want to have just the model in a service, or sometimes you have use cases where you use the model to compute something else, right? So maybe the model has some scoring, and then you do some optimization based on that. And there actually, what you don't want to have the model in a separate case, but the model should be sort of part of another service, and then you just sort of, you don't do this remote call, but you just have it in the system itself. Yeah.
Okay, we still have quite a few questions, but yeah, we already have Sara waiting. So maybe like just a few last ones, and I'm sure you probably get this question that I will ask you right now, like after every talk.
Yes.
But I will still ask you. Can you guess which question is that? No?
How do I draw my figures? I don't know. That's
exactly.
Yes, so I get it so often that I have a blog post on that, which you can find on So I actually do have the blog post. Now I draw them on an iPad with an app called Paper. I think it was called Paper 53, but it's not just Paper.
Okay, so we will add a link to your blog post in the descriptions, and maybe you can mention how people can find you now on the internet.
Yes.
So Twitter, LinkedIn, what else?
Twitter. So Twitter is just Mikio Braun. It's my name. LinkedIn also just my name. I have a blog which is called margin.blog. So marginally interesting.blog. It's maybe a bit hard to find. But
you can start with this name?
Sorry?
How did you come up with this name? Marginally interesting.
No, I had my blog was called Marginally Interesting, like for a long time. I don't know. It was like an early 2000 kind of blog title, because I think I didn't want to have it too specific on a topic. So I just thought if I call it Marginally Interesting, I can write about whatever I want. Yeah, but I like the name, so.
Yeah, I will make sure to include all these links in the description. And thank you very much for joining us today, sharing all this knowledge with us. Yeah, thank you.
Yes,
thank you a lot.
Thanks for having me. Okay.
Yeah, goodbye.
All right. Oh, where do I?
Hey, Sara.
Hello there. Can you hear me?
Yes, but I cannot see you yet.
Okay, 1 second. Just need to start the video.
Oh, great.
Awesome. How is that?
Yeah, it's great. I can see you perfectly. I can hear you well.
share real quick? Is it just us right now, or am I broadcasting?
You are being broadcasted, yes. So, and right
Okay.
now, 68 people are watching us on YouTube.
Okay, awesome.
Yes.
Let me share my screen and just make sure everything is working correctly.
Yeah, great.
So you can see that?
Yes, I can see that. Maybe you can try to move between slides just to make sure it works.
Yeah, one sec. Is that good?
Yeah. Okay.
Cool, you're able to see.
So
Yep.
I suggest to have a small break because you saw that we just finished the previous talk. So yeah, maybe 2-3 minutes of break, and then
Sounds
we will
good.
start with your talk. Yeah.
Okay, great. Just let me know when I should unmute.
Yes. So I'll be back quite soon, and I also want to now tweet that you're live.
Okay, great.
Yeah. So let's start in 2-3 minutes. I'll be right back. Hello.
Hello. Can you hear and see me again?
I can hear you and I can see you.
Awesome.
Yes, thank you very much for joining us today. And this is
Thanks
morning
for
for you,
having me.
right? This is
Yes, it is 10 a.m. Eastern.
yeah, so, well, at least you are not from the other side of the States where it
Oh
means, I
yeah,
think
that
it's
would
like
that would be
7
very
o'clock.
early. Yeah.
It's very difficult to convince people from that time zone to join our events. I can imagine why.
For sure, yeah.
Yeah. Okay, well, I think we're ready to start. So, yeah, the floor is yours, please.
Awesome. Thank you, Alexi, for having me. Great to be here. Hello, everybody. My name is Sara Robinson. Just make sure my slides are all set here. One sec. There we go. I'm going to be talking about machine learning design patterns, which is an O'Reilly book that was published at the end of last year that I wrote with two of my colleagues, Lack and Mike. So I'm a developer advocate at Google Cloud focused on machine learning. So as a developer advocate, my job is to help educate and inspire external developers, customers, and teach them how to use all of the great machine learning tools that we have on Google Cloud. And we do that through live demos, presentations, blog posts, videos, demo code, etc. Another important part of that job is taking feedback from the external community, folks like all of you, and bringing that back to our product teams. So you can find me on Twitter at srobtweets. I also have a personal blog where I blog about machine learning things at sararobinson.dev. I'll link to it at the end. So with that, I'll get started. And I also have a real life copy of the book right here. So what are design patterns? So design patterns is a pretty common term. that's basically just a formalized best practice to solving a common problem. It's definitely not specific to machine learning. Design patterns, have been applied to many different aspects of software engineering and other fields. In this book, we detail 30 different patterns that the three of us have seen after working on machine learning products at Google, working with customers that are using these products. So in this talk, I'm going to be highlighting 3 different patterns. So this is just a quick preview of a diagram that we have in the end of our book that shows the interactions between different patterns. So it's often the case that you wouldn't just use one of these patterns in isolation. A lot of times they go hand in hand with other ones. And I'll talk a bit about the connections between patterns as I go into the 3 that I'll be highlighting today. So the first pattern that I'm going to be talking about is rebalancing. The number 10 is not a mistake here. This is the 10th pattern that we cover in our book. So just to give you a little bit of context of where it fits into the rest. So this pattern is related to getting your data set ready before you train a model. The last 2 patterns that I'll be covering focus more on productionizing machine learning models. So let's start with rebalancing. And in our book, for each pattern, you'll notice if you've read it or if you're in the process of reading it, each pattern follows a similar structure. So we start by defining the problem that a pattern solves, and then the bulk of the section on that pattern is focused on the solution. And then finally, we discuss some trade-offs and alternatives for that pattern. And there is a GitHub repo that's associated with our book. So for any of the patterns, you can go take a look at a notebook, run some code that shows an example of how to implement that particular pattern. So the problem that this rebalancing pattern is solving is that most real-world data sets are not perfectly balanced. So maybe you've seen, like a machine learning tutorial or a Hello World example where you're given a data set that has a nice, neat number of examples per class. So maybe it's a classification problem, and there's exactly 1,000 examples for each class in your classification problem. That's great, but often the case in real-world data is that the data is not going to be balanced. So examples of that are cases like anomaly detection, where you're trying to detect anomaly. The nature of an anomaly is that it's not very common. So this is an extreme example, the one I'm showing on the right. This is just a data set that we've made publicly available in BigQuery, our enterprise data warehouse on Google Cloud. And you can see this is a binary classification data set. So there's 2 classes. This is used to solve a fraud detection problem. So a common case of imbalanced data sets is fraud detection in financial services. So you can see in this data set, this is just showing a count of how many examples per class. Less than 1% of the data contains examples of fraudulent transactions. So one thing to be aware of here is maybe you train a model on this data and don't make any modifications to the data set or model, and you see your model reaches 99% accuracy. That sounds good when you first look at it, but it's likely a case that the model is just randomly guessing the most common class because it occurs 99% of the time. So just something to be aware of. So yeah, we can see that this data set is quite imbalanced. One thing I want to note before I dive into this pattern is there's a few different types of bias. So bias is often a bad thing, but not always. So in this chapter, in this pattern, I'm focusing on what we call naturally occurring bias. So this is bias. These are scenarios where the data that you're dealing with is inherently imbalanced, and it's not possible to go collect future data, further data. So in the case of fraud detection, for example, you notice your data set's imbalanced. That's just the way it is. You can't go collect more fraudulent examples because there are none. Unfair bias occurs when the data you've collected doesn't accurately reflect all the possible people who could be using your model. So an example of this is, you can see with the emojis, let's say you decide to build a model that detects cat breeds, different types of cat breeds. Your model performs really well, you deploy it to production, people start using your app to classify dog breeds, they're uploading their dog photos. Your model wasn't trained on that data, but it's going to give a classification of a cat breed anyway. In this case, this could have been solved by further data collection. So we have a different pattern that focuses on unfair bias called the fairness lens pattern in the last chapter of our book. For this rebalancing pattern, I'm focused on naturally occurring bias. So I touched on this a bit in the first slide, but it's really important when you're dealing with imbalanced data sets to choose the right evaluation metrics. So let's say we finish training our model, we see accuracy is 93%. Maybe for our particular use case, that's okay. We've decided that, if it's above 90, we're okay with that. But the problem with just using that blanket accuracy number as the metric is that you might be missing some problems with your model. So if we look at the accuracy breakdown by classes, we can see that this particular model was only able to classify minority class data correctly 12% of the time. Here I'm just using the word majority class to refer to, this is a binary classification example. So majority class is the class that has the most data available for it. Minority class is the least. So it's really important to make sure you're using the right metrics to evaluate your model. If we were just using accuracy, we might decide it's okay to deploy this model, when in reality, it's not performing very well at all. So now that I've addressed the problem there, what are some techniques for handling imbalanced data? There's many more than what we've detailed here, but these are the three that we focus on in the book: downsampling, upsampling, and weighted classes. So I'll dive a bit into each one. So downsampling. So let's say this is what our data looks like at the start. We have way more examples for a particular majority class. So what downsampling does is you randomly discard a sample of the majority class data. And as you can see, this significantly improves the class balance in your data set. Some things to be aware of with downsampling. In order to do this, it obviously requires that you have a big enough data set to begin with. And when you're doing it, you want to make sure not to lose meaning or relationships that are conveyed in the majority class data, because there's still relationships you want your model to learn about that class. So you don't want to lose important information. So it's important when you downsample that you do that randomly, and that might look different depending on the type of data you're working with. So if you're dealing with data that has a time column, for example, you probably don't want to just remove a chunk of data. If the data is ordered by time, you don't want to remove the last chunk of data, because that's going to take away some meaning from the data set. So you want to be careful about how you randomly discard that data. Just one thing to note about downsampling. So you're left with, ideally, a much better balance of your data. The next technique that we talk about is upsampling. This one is a little bit more complicated than downsampling, but it's essentially the reverse approach. So you start with this very imbalanced data set, and the idea here is that you use the minority class data that you have available, and you generate new data that's based on that. So this new data should be in the same feature space as the existing real data that you have. There's a paper that proposed this technique called SMOTE. It stands for Synthetic Minority Oversampling Technique. Really interesting paper, definitely recommend checking it out. So a simplified example of how it works is this. This is just an example from a data set that predicts, it takes some health metrics on a person and predicts whether or not they'll develop a certain health condition. So on the left, we have two real data points from the minority class of this data. And then we've used that. In this case, we're generating a new synthetic data point that's the median of these two. So a simplified example of how SMOTE works. And there are some Python libraries that can help you do this. So in the case where maybe you wanted to try a downsampling, but you just didn't have enough data available in your initial data set, then SMOTE might be a good technique to give a try. So the last approach for handling imbalanced data that we discuss in the book is weighted classes. So weighted classes, you can imagine this as your minority class speaking to your model saying, pay more attention to me. Obviously a simplified example of how it works, but basically you want to tell your model to assign more weight to the minority class in your data set. And here's an example of how you would do this in Keras. So the way that you determine how much weight your model should assign to given classes is based on the balance of that data set and how that data set, how many examples of each class are in the data set. And then all you need to do in the Keras example is just pass this class weights parameter to your model, and you can assign class weights that way. Other ML frameworks have different ways to do very similar thing. If you want to pass class weights, for example, in XGBoost, PyTorch, there's ways to do that. So to summarize the rebalancing pattern, we talked about 3 techniques for handling imbalanced data. The good news here is that you don't have to use just one. So you could actually use all 3 at once. Let's say you had enough data to do downsampling. So maybe you wanted to downsample, remove a random sample of your majority class data, but not all of it. You could do that. Then you could upsample to account for the remaining data imbalance. And then finally, you could use weighted classes in combination with that. So it's definitely worth trying different ones to see what works best on your data set and what works best for your model. So that is rebalancing. The next pattern that I'm going to talk about is workflow pipeline. And this is pattern number 25 out of 30 in our book. So the idea with workflow pipeline is bridging the gap between model development and deploying a model to production. So when you're developing a model, you're doing data pre-processing, you're validating your data, training your model, deploying it, but you don't just build a machine learning model once, deploy it, and you're done. That's just not how it works. You have to constantly monitor your model, make sure that it's still performing well on new data, handle how you're going to retrain data, new data that becomes available, and use that to feed back into your model training. So you're constantly running a series of experiments. And maybe you don't want to run the entire process again, but maybe you have new data available. So you need to run part of this workflow again. So you need to do data pre-processing, iterate on your model, and train it. Or maybe you just need to retrain your model and deploy a new version because maybe the framework you're using has changed and you want to take advantage of some new features. So it's an iterative process. And when you fix all these small things, it's easy to lose track of all these changes that you've made, especially if you're working as part of a larger team. So, just the end-to-end process in development can work on its own if you're the only person building the system, or there's very few people on your team. But once you start to have a lot of people working on a model or problem and maintaining that model in production, it becomes a little bit unwieldy. So one way you could solve this is you could just take the entire end-to-end process that we talked about, from data preparation to model deployment, and just make it a job, and then just rerun that job whenever you need to. The problem with this is that it can be pretty wasteful. So if you're repeating certain parts of the process many times, for example, to do something like hyperparameter tuning, that can use a lot of compute resources. So it has some wasteful repetition. You don't necessarily need to rerun the hyperparameter tuning step of your workflow every time if you've just collected new data and you want to retrain a version of your model. And so there are some similarities between MLOps and DevOps, but there are also some key differences. So with MLOps, you're not only testing and validating code, because you're doing that as well, but you're testing and validating data, your data schema, and your models. And ML is also concerned with the process of automatically monitoring, retraining, and redeploying models. So you have to take work to ensure that your model is still performing well in production, and take the necessary steps to update the model. And you're also not focused on a single piece of software. You're dealing with an entire end-to-end ML system. So you want to make sure that your workflow is repeatable also. So you want somebody in a different location to be able to rerun your end-to-end ML workflow and have the same outcome. So just highlighting some ways that MLOps adds to DevOps. So to solve this, we have the concept of workflow pipeline, which is the name of this pattern. So here we're looking at a screenshot of the DAG for a pipeline that's running in Kubeflow pipelines. This is just one example. There's many different tools and frameworks you can use to implement ML pipelines. But the key concept here is that it's a directed graph of ML steps. So each step in this pipeline, in this DAG, is a key step in your machine learning workflow. So this is just what the dashboard looks like for an example pipeline that we're running in Kubeflow pipelines. And a key component of this is that each step in your pipeline is its own container. So here we have our container for data pre-processing and validation. We have our container for feature engineering, for training models, for evaluating our models and picking the best one, and then finally for deploying our model. So each of these steps is its own container. And the idea with the pipeline pattern is that you link all of these containers together to create one workflow pipeline. So why would you do this? Why is this helpful? This can help you group all of your steps into a series of experiments. So you can launch this pipeline end to end as a whole. But the important part here is you can also launch individual steps of your pipeline. So maybe you just want to run the hyperparameter tuning step of your pipeline in isolation. You can do that really easily with following this pipeline pattern. And then another important part of what this pipeline pattern does is it allows you to track dependencies from each step as you go through a particular end-to-end pipeline. So these steps are not independent of each other. Each step generates some artifacts and then feeds those artifacts into the next step. And then the next step will look for a particular input. And the idea is that all of these artifacts are stored in a central location so that you can track what was generated from a particular pipeline run. And you can track the artifacts that were generated when someone else ran your pipeline as well. So the hyperparameter tuning step might take the output of the pre-process step, the engineered features, and then feed that into the model for training. So this allows you to reuse artifacts. So maybe if you're only running one step of this pipeline, you can reuse the artifacts that were generated the last time the previous step run, if the data changes. So another benefit of pipeline is this artifact lineage tracking, so that you can see what was generated every time your pipeline runs, and it becomes much easier to manage this way rather than just running ad hoc experiments. So how will you implement this series of containers that you link together? So you could write the code to do that yourself, to handle all the dependency tracking and storing and managing artifacts. But instead, in the book, we recommend using some frameworks that can help you with this. So there's many different pipeline frameworks that you can choose from. Most of them are open source, and these are built to help you with this process. And they also come with many different pre-built containers. So in the workflow pipeline section of the book, we talk about TFX, TensorFlow Extended, an open source framework for building ML pipelines. So you can write the code in Python. You don't have to worry about creating these containers that are underlying each step yourself. The framework will handle that for you. So what TFX does is it also provides a library of pre-built components. So for common things like let's say you want to ingest data from a CSV or ingest data from BigQuery, like we see here. You don't have to worry about writing the boilerplate code to read that data and decide where you're going to store it, etc. Frameworks like TFX will handle that for you. So in this example, TFX has a pre-built BigQuery example generator component, and all you need to do is pass that a query. You can pass it a separate query for your training, your validation, and your test data if they're in separate tables. It'll take care of running that query, grabbing the data, and putting that data in the location you specified for where you want to store the data for your pipeline runs. So the code we see on the top is how we're defining our pipeline. The important piece here is the components. So we define all the different components that make up this pipeline. In this example, all of these components that we're using are pre-built components that are part of TFX. So we just need to provide a couple parameters to those components that are specific to our model or use case. So in this example, our first component is BigQuery generator. This takes care of reading our data from BigQuery as our data source and writing that output to an output file. In the example in the book, we talk about using cloud storage to write that data, but you could store the output of the artifacts of your pipeline wherever you'd like. So then the next step in the pipeline is this statistics generator component. So this will read the data from the BigQuery example generator and give you some overall general statistics on that data that you can see in the dashboard. Finally, that gets fed to a component that generates the schema that will be feeding into our model. We train our model and then we deploy it. You can also have some conditional aspects here. So maybe you only want to deploy a model if it reaches a certain accuracy threshold. So you could then add an evaluation component in between the train and model pusher component. So there's lots of options for customization here. The key idea of the workflow pipeline pattern is that you want to capture your machine learning workflows in a DAG, and this pipeline is executable as a whole or in smaller parts. So if you only want to run maybe 2 or 3 components at once, you can do that as well. One thing I forgot to mention is that in addition to this idea of lineage and artifact tracking, there's also logging and monitoring for each step of your pipeline. So I think I showed in a previous slide, you can see the logs for individual steps right in your pipeline's dashboard. And this is pretty common between different pipeline frameworks. One of the great things about using these open source pipeline frameworks is that you can run your pipeline wherever you'd like. So you could run your pipeline on premise. You could then take the same pipeline code and decide to run it on different cloud providers. So using these open source pipeline frameworks can really help with that. Everything runs as containers, so this ensures repeatability. It also makes it so that, and TFX and many of these frameworks have the ability to obviously write your own custom containers. So if custom pipeline steps, so if the pre-built steps don't do exactly what you want, you can define your own custom step for some custom task you'd like to define in your pipeline. It also kind of separates concerns so that, let's say you're in charge of data collection and feature engineering. You can go off and work on that separately. Maybe the MLOps team that's in charge of deploying your model and running continuous evaluation, they can work on that separately and use different dependencies for those particular steps. And then you can combine that work together into this pipeline. So this allows for more efficient development and productionizing of models and tracking each step of the ML process from end to end. So when you're starting out, maybe it makes sense to just, iterate this workflow on your own within a notebook. But pretty soon after that, I find it really helpful to turn that workflow into a pipeline so that you can more easily share it with others on your team and track the output from certain runs and make it reproducible and repeatable. So that wraps up the workflow pipeline pattern. The last pattern that I'll be covering is feature store, which is the 26th pattern in our book. So what I talked about before with the pipeline pattern, it's common at an organization that's doing a lot of machine learning tasks. You likely won't have just one pipeline that's doing one prediction task. This happens in toy problems, but more likely is your organization is solving many different tasks using machine learning, and these different tasks may be run by different teams. So in production systems, you commonly will have more than one pipeline, more than one prediction task at play. But oftentimes, these different models and prediction tasks will be using the same data. So let's say you have multiple teams building different types of ML models, and let's say they're all running their own pipelines, writing that code from end to end. This ad hoc approach will quickly become kind of unwieldy, mainly because they're not reusing features. So let's say, for example, that you're building a model to predict whether or not a customer will return an item. And as input to that model, you have a feature that's a windowed aggregation of purchase data. So you're using that as a feature, but chances are there's another team that's solving a different prediction task, and they're using that feature too, but they're computing that windowed aggregation on their own, doing it separately in a slightly different way. So in that case, effort and time are wasted because those teams could be sharing that feature engineering code and pulling the features in the same way from your database, but they're not. So that effort is duplicated. So this approach of all these disparate teams building models and engineering features in their own way won't scale. Some other problems that will arise when this happens is you might run into some issues for data governance when you're dealing with sensitive data. So maybe you have data that user data that your ML model is using, and you only want certain teams or certain groups of people to be able to access that data. If you have more than one team doing feature engineering on that data, it's harder to control that. So features are not easily shared between teams or across projects. Another problem that arises when you're not sharing features across these different ML problems is a problem called training serving skew. So ideally, you want the feature engineering techniques that you're using for training your model to be the same as what you're using when you're serving your model in production and taking, doing online near real-time predictions. So you want that feature engineering to be the same so that there aren't inconsistencies between training and serving. So generally, it just becomes difficult to productionize your features, to move from training and serving, and you need a framework that will support low latency inference when you're getting predictions on your model online, but you also want a system that supports high throughput for training when you're dealing with large batches of data that you need to run feature engineering on. So that's the problem that the feature store design pattern is solving. So what is feature store? It's essentially the idea of creating a centralized location to store and document feature data sets. So you can think of the feature store as implementing basic principles of software engineering, like versioning, documentation, and access control. But it's doing this for machine learning features. So there's a few key components to a feature store. I touched on this before, but the first one is that it's able to do both batch and streaming. So you need to be able to store and serve features for low latency inference and serve them very fast. But for training purposes, you're dealing with large batches of data. So you want your feature store in this part, you would put your data in a data warehouse and you would interact with large batches of feature data that way. There's also a metadata layer to many feature stores that lets you version your feature sets. So let's say you have an older version of your model, new data comes along, you come up with a new technique for engineering a particular feature and you want to use that on new models, but you want your old model to continue using the old version of the data. In that case, you can version using this metadata layer that's available in many feature stores. It allows you to version your feature sets. The older models will continue using older versions of the features, and newer models can use the newer versions with the new techniques for feature engineering that you've come up with. So essentially, you can think of a feature store as a dual database. So it's a data warehouse of features for machine learning. But in this case, it has two use cases. So you need to be able to support online inference for prediction, and that needs to be low latency. But you also need to be able to handle doing feature engineering on large batches of data for training your model. So we have this idea of this online database that's interacting directly with your online application, that's pinging your machine learning model. That needs to be able to do this feature engineering very fast in near real time, but then you have this offline database of features, which is what you want to use for running training jobs to train large amounts of data. So we have these two key design characteristics of pretty much any feature store. So you need a tool that processes large engineering jobs quickly, and a way to store features for low latency and high throughput. So you have this offline feature store that handles large batches of features, and then you have this online feature store that will serve a single row of features. So maybe you're converting raw text to embeddings, and you need to feed those embeddings into your text classification model. So in this case, you would use the online feature store when you have a user using your application, entering some text into a text field. Maybe it's auto tagging that text. So you need to be able to do prediction on that one piece of data really fast. In that case, use your online feature store. You don't care as much about low latency when you're running training jobs, because you don't likely need to run those, multiple times a day or even every day. Maybe you're training a new model weekly or monthly. So latency isn't as important in that case. So then you use your offline feature store for model training. So moving along, feature engineering jobs are typically set up using services like Spark, Beam, Apache Flink, Scala, etc. And your offline feature store might use Hive, BigQuery, or Cassandra to store the data. So BigQuery service provided by Google Cloud, and you typically use an enterprise data warehouse for this offline part of your feature store. And then the online feature store optimizes for low latency. And then finally, many features have this metadata layer that you can use to version different sets of features. So in the book, there's a lot of companies have built their own feature store. Some of them have open sourced it. In the example in the book, we talk about a specific open source feature store called Feast. Feast was developed in collaboration by Google Cloud and Gojek. Gojek is a ride sharing company. So for streaming ingestion, Feast uses Apache Beam. For fast online serving of features, it uses an online store called Redis. So you can check out in our GitHub repository for our book. We have examples of how to set up a feature store using Feast. You can also go directly to the GitHub repo for Feast and check out the getting started instructions on there. So just going to show quickly a couple code snippets that show how you would register a feature set in Feast, ingest the data, and read the data. So for this particular example, we're referencing a taxi rides data set that has some lat-long data on taxi ride, the fare, along with some other metadata on the ride. This is a public data set that's available in BigQuery if you're interested in checking it out. And this is what we use in the example in the GitHub repo. So the first step is to connect to a Feast deployment, and then you create your feature set. You connect the feature set to your data. So in this case, we're loading a CSV from Pandas that has our taxi ride data, and we're telling Feast where to load our data from. Then we do our feature engineering, and we infer the features of our feature set from this Pandas data frame that we've specified. We register that feature set. We ingest the features into it. And then the next step is to retrieve our data. So we have two APIs here, one for this online retrieval of data, and then one for getting our batch features. And these are, you can think of these as two entirely separate REST endpoints. But the great thing about using a feature store is that it's going to make sure that both of these features are consistent. So this will help you avoid situations like training serving skew, where you're using a different method to do feature engineering on data for training versus serving. So you have these separate endpoints, a separation of concerns between model training and model serving. But the feature store is making sure that both of these are consistent. So this is the code for how you would do offline batch retrieval of features using Feast. And this code shows how you would do that for online serving of features. So kind of brings us to the end of these 3 patterns from our book. So just to summarize, the first pattern that I talked about was rebalancing. This solves the problem of real-world data sets not being perfectly balanced and how to account for that when you're pre-processing your data and training your model. The 3 techniques I talked about were downsampling, upsampling, and weighted classes. And you don't have to use just one. You can use many of those. There's other solutions for handling imbalanced data as well that weren't covered in the book. And then the second pattern I talked about was workflow pipeline. And the problem this is solving is needing a way to run different end-to-end trials for different steps in your machine learning workflow independently, but at the same time, being able to track the output of each step and have a central artifact store where you're able to see the artifacts that were generated by each step. So the way that you solve this is through workflow pipeline. You make each step of that ML workflow a separate containerized service. Again, there's many libraries that can help you out with that. Kubeflow pipelines and TFX are both great ones. And then you can run that pipeline with a single REST API call. You can also set up triggers. I'm not sure if I mentioned this when I talked about the pipeline pattern. So maybe you want to trigger your pipeline to run end to end whenever you have, let's say, 5,000 new examples of data available. You can set up a trigger that will just run that REST API call to kick off your entire pipeline whenever a certain condition occurs. And then finally, we talked about feature store, which solves the problem of disparate teams all doing feature engineering with the same data on their own, which can be a waste of effort and time and can lead to work stream inefficiency. So the solution there is to create a feature store, which is a centralized location that will store and document your feature data sets to handle both batch use cases for training models and doing feature engineering really fast for online use cases. So quick summary of the 3 patterns I talked about. If you're interested in buying the book, it's available at this bit.ly link. Cool thing about the book is that all the royalties from it are going to Girls Who Code. So we're supporting a great cause. There is a free trial to read online at the URL here. Lack and I are both on Twitter. So if you have questions, want to learn more, questions on the patterns I talked about, reach out to us on there. And finally, we have our GitHub repo that has examples of implementing each of these patterns. So with that, I think we have a few minutes for questions. I'm going to hop back to the Zoom.
Yes. Before I ask you questions, and I want to remind that if you want to ask a question in the live chat, there is a pinned link that you can just click. It will bring you to a slider, and then you can ask any question. But before we do that, I want to announce the winners of your book because we had the raffle.
Oh, awesome.
Yeah, so I want to quickly share my screen and just show you that these 5 people won the book, and I will get in touch with you, and I will ask you for emails, and then you will get a free copy. And you
Congrats,
can
folks.
read, yes, you can read all about these 3 patterns and all the others. Yes, so thanks for taking part, and congratulations. Yes, and thank you very much, O'Reilly, for providing us free copies of the book and supporting this conference in social media. Yes, so now we have a few questions.
Are these in the chat on Zoom, or you're just going to read the questions?
Yeah, I'll read the questions.
Okay, awesome.
Yeah, but maybe before I read the questions, we already have like 5 questions. I have a question of like my own question. I'm curious, like, if you can select 1 or 2 patterns that you would recommend to learn for people who are just starting in data science, which patterns would it be?
That's a great question. Yeah, so we went in the book in such a way that you don't need to read it end to end if you don't want to. You can kind of pick and choose which patterns are relevant to things you're implementing. I'll also note that the book isn't recommended as like an ML 101 book. It assumes some familiarity with basic ML concepts. That being said, some good patterns to get started with are probably patterns like I'm just referencing the book right here. I don't have the 30 patterns memorized, but I would say probably chapter 2 goes into data representation design patterns. And so a lot of the patterns in there will be especially useful if you're new to machine learning. Thinking about how to represent different types of inputs for machine learning. So whether you've got, tabular numerical data, you're dealing with image data, you're working with text data. There is a pattern that talks about how to combine different, let's say you have a model that accepts like text data and tabular data together. So yeah, I would start by looking at that chapter. Another thing you can do is our last chapter. So it's definitely designed to be able to hop around between chapters. The last chapter is a summary chapter, and it talks about some examples of how you could connect different patterns for certain use cases. So it goes through a few common ML use cases like anomaly detection or natural language processing. So you could start there as well and just see which use case looks most interesting to you or matches what you're doing. Choose some of the patterns from there and then jump around. So curious to hear what folks, if you've read it, like which patterns are most helpful to you, which resonated. Great question.
Should they tweet and mention, or how can they let you know about that?
Oh yeah, Twitter's probably the best way. srob tweets, just find me on there. Let me know your favorite pattern. Tag LAC too. We like to hear what readers think of the book.
Yeah. And what would you recommend somebody, like let's say somebody is a data scientist who already knows how to train machine learning models, but they want to move into machine learning engineering, right? So to get more into these engineering aspects, productionizing models, what are the 1 or 2 patterns would you recommend them to focus on? Like, let's say they know the basics of machine learning, but they want to,
Yeah, that's a good question because the book talks about different roles. So it applies to, anyone from a data scientist to an ML engineer who's in charge of deploying models, maintaining them. So I'd recommend probably some of the ML ops patterns for someone who wants to learn more about that. So specific examples, I would say model versioning is a good one. That's the idea of deploying different versions of a model to different REST endpoints. Another really important one I'd say is continued model evaluation, which talks about how to set up a system for ensuring that catching data drift or model drift, which basically just means that your model is no longer fit for purpose because you can't really just train your machine learning model, leave it there and be done. You need to implement some sort of system that's able to see how the model is performing on new data that's coming in to make sure that it's still accurate. So one example is, let's say you have a model that's predicting flight delays, flight patterns, the way that airlines time flights change over time. So if you train a model on 5 years of data from 5 years ago, chances are that that model is not going to be performing well now as companies adapt. So that's just one example. But yeah, I'd say continued model evaluation and model versioning.
Okay, thank you. And then we have quite a few questions. So first question is, what is considered a pattern? So maybe it's a bit of a dumb question, but I want to know what the book encompasses.
No such thing as a dumb question. What is considered a pattern? So a pattern, at least how we define it, is a common practice in machine learning. So some of these patterns, we've gotten this feedback from a few people who've read the book, is they have implemented one of these many times, but they just weren't able to put a name to it. So just things that we've noticed again and again in different machine learning workflows, and we've kind of condensed that into just a best practice for solving a particular task. So I would just say it's a method for solving a particular task. And you saw some examples of the 3 I presented, but but they all follow that similar format. A common task in machine learning. So a lot of these patterns could apply to many different types of models. So something that's widely applicable and fairly common, I would say, is how we define a pattern.
Yes, thank you. And then a related question is, like I first heard about design patterns in programming. And is there any relationship between the software design patterns and machine learning design patterns?
Yeah, I would say they definitely relate. I mean, design patterns, and we talked about this in the intro. Design patterns, that term has been used for many years, and it applies even outside software engineering or tech. You know, design patterns could be applied in the medical field. In probably any industry has a number of common design patterns. There are some connections, I'd say, between, you know, ML specific design patterns and more software engineering design patterns. But I highlighted some of the differences in the workflow pipeline pattern, because MLOps takes some common patterns in DevOps, but adds things to them. So in ML, I'd say the key difference is you not only need to make sure that your code runs correctly, but you need to have this added step of doing all sorts of validation on your data and your model. I like that about ML. It presents an interesting challenge. So even if, you know, let's say you've written your model code, the code is great, it runs perfectly, no errors. But if your data is not good, then you're not going to have a good model, even though the code runs perfectly end to end. So I think ML builds on a lot of the design patterns you might see in software engineering.
And you just answered the question from Alex, who asked what is the reason for separating DevOps and MLOps, and I think you just answered it, right? So maybe you want to add something to that, or you covered that video?
Yeah, I think I covered that. I think, you know, the main differences are additions rather than differences. So it's taking all these DevOps principles, things like continuous integration, continuous deployment, and adding to them. So you also have, in addition to that, you have, you know, continued model evaluation, like I talked about, making sure that your models don't become stale. You know, the meanings of things in your features, or the target variable, the thing you're predicting, might change. So I'd say, yeah, the biggest additions are continued model evaluation and retraining.
Mm-hmm. And versioning, is it something that is also an important part of MLOps, or?
Sorry, what did you say?
Like versioning, like model versioning, data versioning.
Yeah, definitely. We have some patterns on that as well. So we have a pattern on data versioning. It's called bridged schema. This is how you handle updates to your data schema. So not just versioning. So there's the concept of versioning data where the columns haven't changed. In that case, you just have more data that you're dealing with. But this pattern deals with a particular use case of where your schema might change. So the example it goes through is, let's say you have, going with the taxi example, let's say you have a payment type feature in your data set. And historically, the possible values for that were cash or card. But now you have new data available, and there's you're able to get more specific. So instead of cash and card, you have cash, credit card, debit card, or gift card. So this pattern talks about how to handle bridging that new schema with the older schema to train your model. So that's an important one. And then model versioning talks about how you can version your deployed model, so that, you know, clients that want to continue to use the old version can call that endpoint, and then you can deploy new endpoints. And then when they're ready to upgrade, they can use that one. That one's also important because it separates concerns between the data science team and the app development team. So by versioning your model, the team that's in charge of deploying your application and writing that application code, they don't have to worry about, you know, what framework is this model built with? What do the exported model assets look like? All they need to know is there's a new version that's available at this endpoint.
Yes, thank you. Then we have a question about these design patterns in the book. Are these design patterns Google Cloud specific in terms of trying out or not?
Good question. So none of the patterns are Google Cloud specific. When we introduce each pattern, we talk about the problem and the solution, and we're describing that in more higher level situational terms. Because the three of us do work on Google Cloud, when we go through specific implementations of these patterns, you will see a lot of Google Cloud technology that we use to implement them. We use TensorFlow for a lot of the examples, but we also make sure to include some examples with PyTorch, XGBoost, scikit-learn. So no, the patterns themselves are definitely not Google Cloud specific. The specific implementation examples might lean a little bit more towards Google Cloud.
And yeah, I remember even in this presentation, you showed kubeflow pipelines, which is not a part of Google Cloud, right? So this is like an open
right.
source
Yeah,
framework.
kubeflow pipelines is an open source framework for pipelines, along with TFX. So
Yes.
so we do talk about quite a few open source frameworks as well, like Feast also.
Mm-hmm. Yeah, and Feast also runs on other cloud providers, not just Google Cloud, right?
Yeah, definitely. Yeah, so the goal, the way we've set up the book is that, maybe the code snippets become out of date because of a new version of TensorFlow or some service we're using. The ideas behind the patterns still should be very relevant because we talk about them more in, higher level implementation terms of just like when a need for this pattern would arise.
Mm-hmm. And there is a question about this about unbalanced data. Is there any recommendation on algorithm or a design pattern which can work well with unbalanced data without having to rebalance the data?
Oh, interesting. I would say the best solution for that is probably to try weighted classes without downsampling or upsampling, and seeing if that's able to work for your particular use case. Another method could be to change the error metric that you're optimizing for. Because I talked about accuracy as one example, but the way that you choose to measure your model's performance will significantly influence how your model performs. So I'd say, yeah, try switching up the optimization objective and weighted classes, and that might work just fine. You might not need to add or remove data.
And if I may add something from me, is sometimes you can rephrase a problem as a search problem. And then instead of, trying to predict a super skewed, unbalanced, like this positive class or negative class, you kind of try to retrieve it to find it. Sometimes it works, sometimes it doesn't.
That's a great point. We actually have a pattern that covers something related to that called reframing. So that talks about, changing a task from, like you just said, from regression to classification. So maybe you have a regression task where you're predicting a numerical value, but you have not very many examples of outliers on either side. So then instead, just bucket your data into a classification task. That way, all those outliers are grouped together. And there's a good chance your model will perform better at predicting outliers that way.
Okay, thank you. I think we will no longer keep you. So thanks a lot for coming, for joining. Sorry, I keep saying coming, but these days we don't come to events, we join events, guys. We join remotely. So thanks a lot for joining, for spending time with us, for sharing all this knowledge, and for talking about these design patterns. And yeah, thanks a lot.
Thanks for having me, and thanks everybody for joining. Appreciate it. Have a good weekend, everyone.
Goodbye. We now will have a short break before Elle joins. So yeah, in 4-5 minutes we will start again. And let me just share my screen. And see you soon. Hello.
Hey, what's going on?
I am sorry for keeping you waiting.
All good things come to those who wait, huh?
Yeah. So as you see, one of our friends who support this event is O'Reilly, who gave us free books, and MLOps community. And today we have a guest star, like a star appearance. It says MLOps community, but the real name of this person, I don't know if you need any introduction. Okay, now it says the real name.
Yeah,
Okay.
I had to throw it up there. I know for some reason, whenever I jump into Zoom, it automatically calls me MLOps community.
Because you are
Yeah.
the community. Oh, you're not alone, of course.
Yeah, exactly.
Yeah.
I wish I could say that, but there's so many other people that are part of it, including you two amazing
Yes,
people.
of course. Good morning.
Good morning. What's going on, Elle?
Good morning. I rolled out of bed and I'm here. It's 8 in the morning for me. I took the long commute from my bed to my kitchen and I'm ready.
Nice.
So, Demetrius, you are the host, so you have the honors of, do your Demetrius thing.
I love it. First of all, I want to say thanks to Alexi for letting me jump in here and do this because I've been watching the 5-hour marathons, the Friday 5-hour marathons, I guess we could say, for the last couple of weeks, and I just wanted to be a part of it. And he said, "You can come and host one of them." Because we're already full for speakers, and we'll say that MLOps community collaborated. But in all seriousness, I think that what you got going on is pretty awesome, man. You're doing a great job. You are an incredible data scientist and community builder. Who would have thought?
Thank you.
And the other person on this call is also doing a great job. I see Elle doing some incredible stuff when it comes to the advocacy of how to be a better data scientist, how to bring a software engineering mindset into data science, how to do things in a more efficient way when it comes to just ML ops in general, I think. So I'm stoked to be on this call with you and hear what you've got to say. It is going to be a presentation, I think, I hope, because if it's not, I'll prepare some questions real fast, but it's a presentation, right?
Yeah, that's right.
All right, good. All right, so then I will hand it over to you and let you take over and tell us all about what you've came here for.
Cool. Thank you for the intro. That was lovely. So thanks for having me, and I'm just going to jump right in. So a little bit about me. So for most of the last decade, I worked in academic research in various areas of neuroscience. And one constant in my work is that I always do a lot of mathematical modeling, and I really enjoy excuses to use very big computers. And when I got my PhD last November, actually now it's more than one November ago, I was interested in how scientists in academia and industry use computers and how we're going to build tools that enable high quality science as our methods and data sets and problems all seem to be getting more complex. So I signed on as a data scientist at Iterative.ai, and we're a small company that our flagship project is open source software called Data Version Control, or DVC. DVC is a tool that adapts version control systems like Git to data science. So we're kind of at the intersection of data science and DevOps. And one thing to note is that this is actually my last full day at Iterative. I'm joining the faculty at the University of Michigan School of Information. And so I will still remain involved in advocacy work and such. But my capacity is as a lecturer and research investigator here. So I'm really excited, and we're working on putting together an applied, we have an applied data science program and incorporating some of these tools into, the education that a data scientist will get. So today I'm going to share a little bit about some of the ideas that are, have been on our minds for the last couple months, and a project that I'm really proud of coming out of Iterative. It's like a sister project to DVC. So I want to set the mood with a figure from a really strong case study.
I wanted to ask if you're sharing something with us right now.
I should be. Oh no. Okay. Here we go. There we go.
There it is.
Well, you didn't miss very much, other than that I had a slide that looked like this. It was extremely basic. Thank you for that. Okay, now I'm going to start with a figure. So this is a figure from one of my favorite case studies. It's a study of teams across Microsoft, and the authors are reporting that teams, whether they work on speech or search or ads, as long as there's some machine learning component involved in the workflow, they tend to follow a pretty similar workflow on these software projects. We've got, nine steps here. Let's see, so we've got these steps here, and there's a lot of them, and we see some loops here. This might look kind of familiar to anybody that has worked on a data science project, even if it's a quite small one and you're not working on a Microsoft team on a product that's going to ship. This is kind of recognizable. And of course, there are a bunch of folks with different skill sets working on this. We have data engineers, symbolized by this happy, adorable piggy, collecting, cleaning, and labeling data. Data scientists are engineering features and then training and evaluating models. And software engineers are deploying and monitoring applications built around those models. And this organization is full of baby animals, and this is my ideal company. So I just wanted to share that with you all. Anyway, this is all fine if the project is linear, like a relay race, but it's almost never that way. So we know that excellent machine learning models rely on feedback, which means software engineers and data scientists might have to pass several modeling experiments back and forth. Plus, there's often, a big hit in your model's performance after your model's been in production for a little bit, concept drift and such. So we need some refinement over time. Data scientists need to be able to anticipate the system constraints of software engineers who will deploy their models, or you end up with the situation where you've developed something in your Jupyter notebook and then it won't work anywhere else in your production system. And everybody needs to be able to trace where your data came from, particularly if there's got to be some kind of audit. There are certain domains where this is even more essential, but I would argue it's essential everywhere because models are defined by the data they're trained on. And all of this back and forth can get very confusing very quickly. Now, even though machine learning is a new part of software engineering workflows, and it isn't always easy to incorporate, software engineering isn't a new discipline, on its own. We've had some time to learn. And in the field of DevOps, or, we've got development, operations, portmanteau, put them together, DevOps. This might have some lessons for us. So specifically, DevOps has had success bringing together developers and operations specialists. So there's some reason to hope that, maybe if we look at how this has worked out and what kind of practices have taken hold here, we can, find some common ground for engineers and data scientists too. And so I want to talk about the principle of continuous integration and delivery, which is one of the coolest and most important, core concepts in DevOps. And it's really changed the way that multidisciplinary teams run, is continuous integration, delivery, abbreviated CI/CD. So CI/CD is a practice that establishes collaboration rules between developers and operations specialists. So it's more of a culture than it is a specific technology, but it generally goes a bit like this. So when somebody makes a change in your source code for your project, a build will happen automatically, and then some tests will get run on that build. And if the build passes the test, the modified source code becomes a candidate to be merged into the main branch of your project. And the idea is that every action, like a git commit and then push, triggers feedback, and every round of feedback will produce a release candidate. So you're getting fast automatic tests and frequent feedback. And everybody on the team who can touch the code has access to this information. You don't have to wait for somebody else to come and test your code for you. So let's take a look at what's different when machine learning is part of the workflow. So we can now, instead of changing code, we also have to worry about changing data, because your machine learning model is influenced by your data, probably even more than your code. Data matters a lot. So if you change your data, you've changed your model. So it's no longer enough to just, track changes in code. In addition, we're not just building software, we're training models, and that can have some specialized requirements. You might need a high CPU, high RAM instance for that, or you might need a GPU. The hardware here can be a little bit different. And now, instead of just getting these kind of pass-fail answers back, we're evaluating a model, and we'll often get a summary of many different metrics. And if a model has improved, can be kind of subjective, or at least it's not easy to define unless you really know the domain. So for example, a model might go up on overall accuracy, but at the expense of some precision. And if that is acceptable for your use case, can require a data scientist to say, yeah, this is okay. So there are a few reasons why these kind of modifications aren't trivial for existing CI/CD systems. One is that version control can't always track changes in data sets. So data sets, which are frequently on the order of a gigabyte, 100 gigabytes, they don't fit in your Git repository, and Git tracking code is very commonly the way that, these changes trigger the CI loop. So data sets, versioning them is a problem. Then training models isn't like building software. It's, if you need a GPU, if you need an EC2 instance, then that is a barrier. And evaluating metrics is just more complicated. So what is pass-fail? It might mean, we might need quite a lot of metrics summarized to get a real good picture of what's going on here. So what's going to be needed are tools that will extend these CI/CD practices from the domain of software engineering to machine learning. At least this is what I think is needed. And this is something that we're thinking about as we continue to develop DBC. And we're people that make tools. So I want to show you a tool approach that we've made, for introducing some of these changes. So here's a wish list for some of the features that we might want and that we set out to make if CI/CD is going to work for ML. We want to be able to version data like code. We want our CI system to be able to allocate whatever hardware is needed to train models. And we want metrics about model performance to be reported in a human readable format so data scientists and other team members can efficiently review them. So the work I'm going to show you is a collaboration with Dmitry Petrov, who's a DBC creator and co-founder of our company, David Ortega, developer, me, a data scientist. So, knowing what we want, how are we going to do it? Our team is really into the Git ecosystem, and we like Git tools because they're so well established in the software development community, and we think they can be adapted to work better for data science projects. So two services in particular have really caught our attention, and that's GitHub Actions and GitLab CI. These are systems designed for Git-centric continuous integration. And there's a tremendous overlap in what you can do with GitHub Actions and GitLab CI. So for the most part, I'm going to focus on GitHub Actions in this talk, but please keep in mind that everything I say and show you, you can also do with GitLab CI. So the project that we're working on is called Continuous Machine Learning. Two ways to follow our project. We have a GitHub repo, just kind of like the hub. We have a website, cml.dev. And so to kind of revisit this figure and show you where CML, continuous machine learning, fits in, this is the idea. GitHub Actions can help us with this part of the CI process. So automating model training and testing is something that GitHub Actions can do. And GitHub Actions is, it basically is a service that runs a workflow defined by you every time a triggering event happens, like a change is pushed to your project repository. And by default, the workflow would be run on runner machines provided by GitHub, but you can use your own machines too. We'll revisit that in a bit. And so CML is a library that's going to work with GitHub Actions or GitLab CI, kind of on this part of the of the workflow or the CI loop, to make GitHub Actions or GitLab CI work easier for data science projects. So I'm going to take us through the priorities that we laid out one by one and show you how we've handled them. So first, let's talk about providing feedback in the form of metric reports. So let's say we have a project on GitHub. We're using GitHub Actions to automate training and evaluating a model. We're going to create this YAML file in a special file path. It's always going to be in this .github workflows file, but you can call it whatever you want. And this is the secret sauce for any GitHub action. And here's where we lay out the workflow that would be carried out every time our repository detects a push. And, of course, some changes in the push. So a couple things to note here. We are going to pull a Docker container. We've got some triggers. So the trigger here is push. There's our Docker container. The Docker container is our Docker container. It's not special. You can do this without our Docker container too if you install some of the dependencies, but just for compactness, I'm showing you this with our Docker container. And so it's got Python, a couple other things that are nice to have for a data science project, and the CML functions. And here in the workflow, so we're going to say, okay, every time we've detected a change, we're going to run this Python train.py, so train a model. And then I'm doing some bash scripting here. And what it does is it's going to write a markdown report of things that are output by this training script. And I'm using some special CML functions, CML publish and CML send comment, that are going to help take outputs of our Python training script, which in this case are a text file full of model metrics and a confusion matrix, so evaluating on some test set data, and we're going to publish them. And what that looks like is that when you make a pull request, you get a report. And so here we have our model metrics. We have a visual. This is just a scikit-learn visual. It's not special. So this is a way that you're getting comments. You're getting, reports about what's going on your runner in this visual format in your pull request. And so the hope is that this will make, what's going on in your, the machine learning aspect of your project, make sure you don't have regressions, make sure you like this change before you merge it into main, give you and your team a chance to discuss, give a bit more visibility to ways that the model may be changing. So let's take a closer look at what exactly gets run in the workflow. We have a training script that outputs a text file of metrics and a confusion matrix. Then we do some bash scripting with our helper functions to add the reported model accuracy and the confusion matrix to the report. And then we deliver that report, this markdown document, to the pull request as a comment. And here's another example where I'm using DVC to make a table comparing model performance metrics from the latest experiment with what's on the main branch of my project. So DVC has a function where it kind of is like giving you a git diff, but it's for model metrics, so that if you're specifying, if you have a machine learning model and it's being developed on multiple branches or commits of your project, you can, compare its performance. So what are some model metrics like accuracy, loss across different commits? So just sort of like a git diff, but for those metrics. So here what we're doing is we're using DVC metrics diff to calculate how metrics differ across branches of the project. And we're using DVC plots, and DVC plots are actually just a wrapper for Vega Lite plots. So DVC plots, and by that I mean Vega Lite plots, so comparing loss functions between branches. So what's on main and what's at the head of this branch. And so this table gets output to your pull request. So this is actually giving you a comparison. So previously we saw just, what's happening here. And this is actually a comparison between what's on the pull request and what's on your main. Here's another example with TensorBoard. So we wrote a helper function so that you'll get a link to your tensorboard.dev page where you can track your model training in real time. So even though your model is being trained on a runner, you can watch it, through a TensorBoard. So the point is that there's a ton of flexibility here. You can pretty much put anything that can go in a GitHub Markdown document into your pull request as a comment. So you could make your plots or your tables using whatever visualization library you prefer. So you could use Seaborn or ggplot or Vega or whatever. And likewise, any way of writing a table too. And even though the examples I've shown are Python, you do not have to use Python. It's all language agnostic. It's quite high level. You put files into the pull request. So you have a lot of leeway. So a couple ways that, we imagine these CML comments being used is, you can report about model training on remote machines. It gives you the possibility of defining like a really transparent, test result. So you could potentially put, you could put as many metrics as you want on one of these. And we hope it gives you some of the ability to review data and models like code. And we have a video series. I have to promote my video series here. I've been working on a video series. And so these are all use cases, and we make them each use cases into videos. And if you have a use case that you think is interesting and that you don't see represented here, just please ping me and maybe we can make one about it. So this is a way that we kind of give tutorials for these various ways of using it. So if you want to learn more, the videos are there to kind of be like demos. I think when I'm not even sure, this number might have changed, but we've got around 50,000 views on that. So it's going pretty well. Okay, priority. The next priority that we had was that we wanted to be able to version data like code. And we actually kind of have this because we previously developed DVC. So this is kind of a little intro to what DVC does. And DVC and CML are kind of separate open source projects. They don't have to be used together, but using DVC here kind of lets CML be, in my opinion, its most powerful, but you don't have to. But if you want to use DVC, this is kind of how it works. And it kind of had to come before CML because of this kind of data versioning is really important for CI/CD to work. So we wanted to be able to version data like code, and DVC helps us do this. So to be very clear about DVC, DVC extends Git version control. It is not a replacement for Git. You need Git to use DVC. So people ask me all the time if it's a replacement. It's not. It works with Git. So if you have a data set or a trained model file that would be prohibitively large for hosting on GitHub, you could track it with DVC. And the syntax is intentionally very similar to Git. You would add and push it. And here's what happens when you push. You pick whatever kind of cloud storage you like, or it could just be, it could just be a regular file server that you have ran locally. But you pick some storage that you'd like to be a data remote. So kind of like how you have a Git remote that's for your code, you're going to have a separate remote that's for your data. And it could also be models, just anything big. And DVC will coordinate sending a copy of your data to that remote. And on your local machine, DVC creates this lightweight metadata file that can be tracked with Git. This is a sample file, and it contains a hash that indexes the version of the data set as well as points to its location in cloud storage. So to use this with GitHub Actions, you have to pass some credentials to the workflow, which you can store as secrets, or in GitLab, these would be your CI/CD variables. Basically, we just need credentials. So if your DVC data remote is an S3 bucket, we just have to pass some credentials to your workflow, so that the runner can push and pull to that bucket. And then after you've set those up, you can set your workflow to run commands like DVC, pull, and push. So here's what's going on in this workflow. First, we are pulling data. We're going to go from the cloud. We're going to grab a CSV and we're going to give it to the runner. So this is whatever machine is running your GitHub action. Then you might reproduce a workflow. So DVC repro is kind of like a make file. It's a DVC convention for linking together data sets, code, and model files, plus some parameters, turning it into a pipeline. But you can think of it a lot like a make file too. And then finally, we will do DVC push your trained model, and that goes to the cloud. So you can use this to track files, models and data sets that never get stored in your GitHub repository, so you're not beholden to those file size limits. And so a lot of people, some people prefer LFS, but some people prefer this because you can use it with whatever storage you want. It's just like you don't need a server. It's just your Google Drive or your S3 bucket, whatever. And so some of the consequences for this is that changes in your data set can trigger a GitHub action, even if that data set itself is DVC tracked, not Git tracked. So if your data set changed and then you do DVC add to, kind of record that, then that will update the meta file that is Git versioned. So basically now you can use this as a way to trigger a workflow, even though you don't have to stick your data file in your Git repository. Likewise, GitHub Actions can push and pull big artifacts to cloud storage. And that DVC push and pull is kind of a nice high level way of interfacing. So you don't have to write out the address of your bucket or anything. You don't have to hard code things. You can just use DVC push and pull. And data and model versions are linked to every model training run. So when you use this, you'll never have to worry about, okay, when I did this run, what was the state of the data set at this time? Because you have it versioned. And a potential benefit, because if we're using cloud storage, it gets closer to having, less servers. So if you're using a bucket, then you're not maintaining a file server. Although according to the warranty, GitHub Actions is not serverless, please note. So the third priority that I wanted to talk about was that we wanted to be able to allocate cloud resources to train models. And in our first release of CML, we did this with Docker machine, and it's really cool. And so the original idea here was that by using Docker machine, you can create a GitHub action that launches instances whenever a workflow is triggered. And so that means that you can, have a workflow that will actually launch an EC2 instance. And it could be like EC2 with GPU or whatever you want. And then your job will run on that instance. And the idea here was that we could push to initiate training in the cloud. And so to me, it's really cool. This is probably my favorite part. So you can provision and deploy the cloud resources of your choice, run your training job on them, and then your entire training setup is codified. And we're working on an upgrade to this, which is using Terraform. So Docker Machine is actually a deprecated project, and this is being redone with Terraform. And it's really, really cool. And in fact, we just did a pre-release. So the release has not happened yet, but we did a pre-release. And I would really like to show you very quickly what it looks like. It's so new. So what this will look like in your workflow is that you can use this function CML runner. And CML runner, this is all it takes. And this is launching, okay, on AWS, I want to be in this region. This is the type that I want. And this is just a label. So CML, I want in my dashboard, these instances will be labeled with this. And then you run a workflow. And so for this workflow, what I'm doing is I'm just setting up Python and then I'm running training. And so basically this is all it takes to provision and deploy an instance on whatever you like. And then, you can also add in CML functions. So then you can send something back from that EC2 instance to your pull request. So this is an example where we're doing that. You get a report from your EC2 instance. And And you can also do this with a GPU. So let me show you. This has also not been released yet, but I just really want to show you. So this is the code now to get a GPU. So I'm asking for this G3 instance, and then we're using it to train a style transfer model. Let's see, I think I have a pull request with this. Yeah, so we're doing a style transfer model. This last one I did, there's not much of a difference in the style at all, but you can adjust some parameters, you can get the info from your GPU, and you can compare, what does the style transfer look like on the different branches of your project. So what I'm really excited about is just like this, it's just a neat wrapper, and I can brag about it because it was made by David, not me. David is our developer, and I just think he did a beautiful job getting to a very high level place for provisioning these instances. Okay, hang on one sec. All right, there we go. So this is the example I showed, and previously this was about 30 lines of code longer than it will be now. Now everything is just this one CML runner, and you don't have to do anything with Docker machine. It's gotten very, very well wrapped. And this works, we're going to release this CML 0.3.0 release will come with Azure and AWS. So GCP is not supported yet, but it is, of course, on the roadmap. And this is in pre-release right now. So we're happy if you want to try it and report back to us about any bugs you find or things you wish were different. And another thing I really like about this is that your GPUs will turn off at the end. So you can set a timeout on them, at which point, if they don't get any more signals from GitHub or GitLab, they will turn off. So you don't have to be in your dashboard, and remember to turn anything off. And so, okay, so I want to show a use case now, actually zooming quite back out from, the GPUs and how cool I think that is. And this is a use case that I made with Jeremy Jordan, who's a data scientist and software engineer. And so we were inspired by this paper, Beyond Accuracy, Behavioral Testing of NLP Models with Checklist. And so this is, in my opinion, just a great paper. I was at the ACL meeting, and I think it won Best Paper Award. And the idea is that, you can have like a checklist of things that, does your model meet these requirements? And they can be things for, robustness to noise. It could be, how do they perform if we swap the genders of people in sentences? Kind of a way just to get a holistic picture of the behavior of your model, going beyond just reporting accuracy, beyond accuracy, as they say. So we took a test from this, and the idea is that we're writing a test for studying a trained NLP model. The test is given some sentence A, like, I just love the new Honda I bought from Crystal. We could introduce a random typo to get this sentence A prime. So here I'm swapping, putting in right here, just a typo. There we go. And then we can check for if we have a sentiment classifier, for example, and the model is this classifier F, we can test, okay, do we get the same sentiment predicted for these two sentences? We shouldn't expect it to drift that much on the basis of random perturbations. And if it does, then maybe it's not that robust, or it's maybe deciding on some really arbitrary features that we don't really think are compelling reasons to be deciding the sentiment. And so what we can do is now we made a workflow where we're going to run this test on a trained model. So here, we're not model training, we're only model evaluating. And so this is kind of an idea of maybe you did the training somewhere else or at another stage in the workflow. And then, you get to this point where you have a model and you basically want to make sure that you haven't regressed relative to what's on the main branch of the project. So here we're showing an example of switching an Albert model to a Distilbert model. These are just different flavors of tiny BERT being a very popular model in NLP right now. And so we run the test and we're reporting, the differences in performance. And we can see that we have very minimal changes in things like the accuracy. So, it doesn't look like we've regressed, even though we tried using this other model. And then we can print out some failure modes. So we can see examples where we added perturbations and the model changed its answer for what is the sentiment here. And it was just really catastrophically wrong, and it was very confident about being wrong. So like, for example, this sentence here, like such an inspiring car, the way it's perturbed, I think I could see that as potentially confusing. But then some of the other ones are really interesting, like the sales department is about as helpful, knowledgeable, and straightforward as I've ever seen at a car dealership. And here all that changed is we added a Z, and that's interesting why that suddenly flipped everything, why this Z overrules like the helpful, knowledgeable, and straightforward. I don't know, that would be something I'd want to investigate maybe. So that's our use case that we're proud of. And you could also kind of imagine this transfer to other domains, maybe like if you have, computer vision, maybe you're doing image segmentation, maybe we can print out some of the failure modes here, or we could get exemplars from different slices or categories of your data, and you have this kind of visual. So if you go kind of back to the beginning, we had some goals for reimagining CI/CD. We wanted to be able to version data like code. And we are using our other tool, DVC, for this. So DVC extends Git version control to data sets, and that kind of lays the groundwork for, for using CI/CD systems with data science projects. We wanted to let CI systems allocate cloud resources to train models. And, we've built this way, the CML runner function, to deploy cloud resources from GitHub Actions. And we wanted to provide feedback in the form of metric reports. So we have helper functions like these CML publish, CML send comment for writing reports to a pull request. And, all of this gives everybody on your team access to all of your, your data set, your models, your code. And, I think it's a great way to put everybody, having some shared conventions and shared places to test, to experiment, and, to keep models and data sets. And so this is, it's a bit of it's not just a tool. I mean, it's partially a tool, but it also represents, I think, like a shift in, what is a data scientist's responsibilities, and can they have, part of the model, the testing, regression testing, kind of treating it like software, and can they be in that flow too? And I think there's a lot of data scientists for whom that answer is yes. So thanks for listening. Follow us on social for more updates. And then I'm also interested always in collaboration. So if you'd like to collaborate, my research interests are software and infrastructure, data science research, effective teaching tools for junior data scientists, and methods for collaboration across research institutions. And since I'm a research investigator now, I have even more freedom than ever to pursue these things and grants. So just wanted to flag that for anybody listening. But yeah, please follow us on social. We're an active open source project. We would love to hear from you. Open an issue. Tell us what you like, what you don't like. Feature requests, always welcome. If you don't understand something, also tell us that. That's good feedback too. So thank you very much for coming to my talk. And I think this is a good point to take some questions.
All right. We've got some great questions in the Slido, if I'm pronouncing that correctly. Hopefully I am. The first one that I think we should talk about, and some of these you kind of touched on, so feel free to say, yeah, I think I've talked about that enough. But the first one I think is, what do you do when data is too large to download each time when runners are triggered?
Yep, that's a good question. And so we don't have like a special CML tool for this, but there are some ways that we're seeing, we're having some discussions with users who are facing this, and we're getting some ideas. And so if your data set is changing constantly, like every run it might be different, then you do want to download it every time, because that's kind of the only way to, really test it. But if your data set is static, then downloading like a few gigs of data every time you want to run can be pretty tiring and run up your budget, and it's not really worth it. So there's a couple ways to do this. You can, I mean, if you have a self-hosted runner, so a runner, like just a machine that you manage to be your runner, you could put this on like an EBS volume and just kind of mount it there. So it's like always accessible to the runner on a file path. If you're using DVC, DVC has a cache, so it can remember things that have been previously downloaded and prevent you from downloading them. And so as long as you are, you know, always working on the same, as long as the cache is available to the runner and the data set hasn't changed, that would prevent you from doing this. So what you'd want is a self-hosted runner that you can configure to have access to the data locally so that you're not downloading it. So there are ways to do this. But in terms of a best practice, I think this is still kind of exploratory. So if you try this, I would really be interested to hear what worked and what didn't for you. And we also have some discussions about this on our Discord channel too. So that's another place worth dropping in.
Yeah, check out the Discord channel. Where can we find that? Do you have a link? We'll throw it in.
I don't
Throw
have
it
a
in the
link, but I think
description
it's,
or something.
yeah, I can do that. I can do that.
Yeah, for all those people that want to, or just Google search Discord DVC, and you'll probably be able to find it. So the next question we got here is, does CML work better for tracking experimentation or more for final pull request review when all the experimentation is done and you're ready to merge?
Yeah, that's another question that it can be kind of up to you and your preferences. So for some people, having a Git commit for every experiment, they don't like it. Some people are fine with that. Other people think it clogs up their Git history and they don't like it. So that's kind of up to you. I don't think CML was designed primarily as an experiment tracker. You know, there are other tools for that. So DVC has an experiment tracker. There's plenty of experiment trackers out there too, like weights and biases and such, MLflow. And so actually CML is compatible with all of those. Like you can use whatever experiment tracker you like. And then kind of as this questioner alluded to, you could decide, I want to do all of my, you know, I want to tune my hyperparameters basically using like MLflow. And then I'm going to check in my final result of the day. And then maybe we will test it in a container and run some standardized tests and print it out, you know, in our GitHub repository. So either workflow is completely acceptable. And I do see quite a lot of people that don't want to do this for model, you know, searching the parameter space. And I think a good reason, you know, to consider doing a lot of exploration locally is that, you know, this is just slower than, you know, running something locally. Like if you have a job, it's faster, you know, unless we're at like the limits of jobs that take like, you know, a long time to run, like several hours, then it doesn't really matter. But when you're doing things that are kind of interactive and fast, like let me try this and see what happens to the accuracy, that like fast iteration is probably better when you can just like, you know, do that locally, because here there's always going to be, you know, some extra time for setting up the runner and such. It's just slower. Like things that might take, you know, a second or two are going to take GitHub Actions or GitLab CI like maybe a minute, you know, and that's just a general feature of anything that they'll do, not CML specifically. So I hope that helped a bit.
It did for me. Next question we got up, which has been highly upvoted. How do you manage CI config files when the data scientists are trying out different experiments, e.g. changes to metrics or any default outputs?
Interesting. Is there an example of like what kind of config file they're talking about?
Ooh, there isn't in here. And I think there's a bit of a delay. So by the time this gets to them and then they put it into the chat, and then it gets back to them with the answer, it's going to be delayed. But
if you have any guesses, because I don't think I've worked on a project that had like a data science config file. I don't think I know what that means exactly.
Interesting. Well, let's answer the next question. And then if they throw it in the questions while we're answering the next question, then we can answer it. So the Next question on this list is, how would you recommend to get started with CI/CD pipelines? I want to learn more about them.
Yeah, okay, great question. I think the GitHub Actions getting started docs are really good. You can kind of get started with this without using anything data science. Like you can just make a pipeline that like is every time you run your code, it's going to, every time you push a commit, is what I mean, you're going to verify that like 2 + 2 still equals 4. Like you can do things like that and just start getting the hang of like getting this kind of feedback. And then of course, I think my videos are a good way to learn. So we have a getting started video where we do like, you know, I think it's pretty gentle and it's about if you've never seen this before, what it's like, because it's just kind of a new way of thinking, but it's really, really cool once you get started. So it's totally worth learning. So I would say the GitHub Actions getting started docs or my videos, I think are 2 places I might recommend.
I will second your videos for a great pace to learn. You do not need to be so shy about letting people know to check them out because they're awesome videos, and you can tell by the way that the community and people have been watching them and eating them up. I think they add a lot of value, and it is, like you say, it's a great way to understand the framework and the way of thinking. So there is another question that you answered. It is, can I use CML without DVC? And I'm going to take a stab at that and say, yes, you can, but CML works better with DVC.
Yeah,
right?
yeah, I mean, it's not necessary. Like if you don't need it for the data versioning capacity, like that's kind of what DVC does. You don't have to. I mean, if you're using Git LFS and you're happy with that, you can use that with CML. Or, you know, there are other, like if you don't like DVC's experiment manager, you can pair this with another kind of, you know, experiment manager too. So they're definitely meant to be modular. I do think the real reason to use DVC and CML is because I think DVC really gracefully handles doing diffs across branches. So when you want to compare model metrics across branches, you want a table, you want a graph like that, like you can do that with some kind of ugly low-level scripting, but I think DVC does that at a nice high level, and I just think it's the smoothest interface for that.
So the latest question that just came through is about the competition for DVC, and this is always an interesting one. I'm going to see how you gracefully handle this question, Elle, as a enthusiast for DVC, and they're keeping food and the lights on. Everyone knows that you are very much for DVC and CML, but what are some other tools out there?
Yeah, okay. So there are a lot in this space. You know, there's a lot that's worth experimenting with. So DVC, as I've mentioned, if you're interested in an experiment manager, so something that's going to track like all of the different configurations that you've tried, you know, there I think you want to check out MLflow, Comet ML. I mean, there's actually quite a lot in this space. And so, you know, there's weights and biases.
Neptune, I think, does it. Neptune. AI.
Yeah.
Weights
and
and biases.
Yeah, they all kind of have like a slightly different philosophy. And so I kind of feel like if one of them resonates with you, that's the one you should use, because like, I mean, you should do the thing that you're going to stick with, and you're going to actually record what you did in. I think DVC is kind of distinct from a lot of them in that it's, I mean, part of it is that like it's really modular. Like I think one of the reasons that we have DVC and CML and they're separate and they don't have to be used together is that we kind of like modular projects, whereas something like MLflow, like I do think MLflow covers a lot of like the model testing, you know, and getting you closer to production. Like they do that too. They just have a different philosophy for how they're going to do that. And they do it through a platform. And so that's going to work for some teams. And for ours is more about like, no platform. We're just going to have these modular tools and you mix and match them with whatever other tools you have in your stack. So, this might work well for teams that already have like a really strong Git flow, or they love continuous integration through, some of these CI platforms that we've talked about. Like if that's already part of your software stack, then we think this can work. And if that's not a thing you like, then you might prefer the ML flow end-to-end experience.
So that begs the final question from me. What ways have you seen this being used in the stack? Like, what are some other pieces of the stack that you've seen this being used well with?
Okay, so something really interesting to me is, so this capacity to write a comment, like a detailed comment. I was talking to a team where they use it, but not for machine learning at all. They just like the ability to write detailed comments after running a GitHub action. So they were doing like speed tests, and then they would publish that to their pull request with CML, which is so interesting to me. So we, in fact, we have made CML, we're also releasing in the pre-release a GitHub action. So it's like even smaller than ever, and you can just get the CML functions and like nothing else. So I suspect like we'll be seeing more people using it, because I'm like, I don't do data science really at all. I just want to write pretty pull requests.
Oh, wow. Awesome. So last question, I guess somebody slipped one in on me. I wanted to be the last one, but they're wondering, does CML and DVC work for model and data monitoring purposes as well?
We definitely did not develop it with that in mind. I think you could, but it's kind of an off-label use. There's nothing wrong with that. Everything we do is just like engineering it together, from a small team. And if you were to do that and you showed us, we would love it and think it's really cool. But we don't have our eyes on the monitoring aspect of the life cycle. We're really about development here, and that's what we were optimizing for. So in that way, I think you could, but you would be venturing into some uncharted territory there.
Use at your own risk. I love it. I really appreciate you taking the time to do this and school us on this. And I guess that's it. Those are all the questions. So
thanks. And if this person with a config question, feel free to email me. I'm sorry that I'm not able to answer that.
yeah, it looks like we never got anything back about the CI config files when the data scientists are. We'll get that another time. They'll reach out, and then you can do a whole presentation on that.
Yes.
Thank you. And I think Alexi's in here somewhere, or did he go?
Yes, I'm here.
There?
I was thinking actually, like you've been handling this, you handled that so well, so maybe I should ask you to do it more often.
Who are you talking about, Elle or me?
Well, actually, I was thinking about you, Demetrius, but yeah, who knows? If Elle, you are looking for some side activities, let me know.
Yeah, y'all are great hosts. I feel like I'm having like the radio talk show experience here.
The data science radio talk show experience. That's what you get with Alexi's community, the DataTalks.Club. So cool, man. Well, I thank you for giving me this opportunity. And thanks again, Elle. I learned a bunch, even though I've been watching the videos. I kind of knew most of it.
All right. Bye.
Yeah, thanks. Bye. Goodbye, everyone.